Disclaimer cause all materials in this video are for educational purpose only.
Recommendation has become one of the most important applications of machine learning technology on the web. It helps people navigate the explosion of information available at their fingertips. But it also gives machines a tremendous responsibility. That's because we are delegating to the machines the job of deciding whether or not something is worthy of our attention. Some of the earlier recommendation systems to appear were developed by machine learning researchers to support machine learning research. By 2010, Rich Zimmel was program co-chair for a highly influential machine learning conference called Neural Information Processing Systems, known as NeurIPS. His team at the University of Toronto wanted a better way to solve the problem of assigning appropriate reviewers to submitted papers. So they created the Toronto Paper Matching System to help automate the process. It was a hit. By 2013, the service had been picked up by many of the major artificial intelligence, machine learning, and computer vision conferences. And just in time, the number of submissions to the top machine learning conferences was exploding. The Association for the Advancement of Artificial Intelligence conference got more than 1,000 submissions for the first time in 2014. For the 2020 conference, there were just shy of 10,000 submissions. I was one of the reviewers for the 2020 conference. Like all the other reviewers, that meant I had to flag a set of 50 or so of those papers that I'd be well suited to review. So the chairs of the conference could assign each of us 6 to 8 papers and each paper 3 reviewers. I had to pick 50 papers out of 10,000. Even focusing in on the most relevant keywords, it was quite daunting. If only there was some way to get a computer to help identify the papers that were likely to be a good match for me. That might save a lot of effort. It's much more manageable if the computer can present me with 100 or so titles, and I mark half of those as topics I'm well informed about. Identifying papers to review is one example of the more generic recommendation problem. We want to make programs that can sift through many items on behalf of a group of people to find items that each person should look at more closely. The items could be web pages, or movies, or apps, or news articles, or restaurants. And these recommendation systems are more than just labor-saving devices. They select what items users see most easily. As a result, recommendation systems color our perception of reality. In general, the recommendation problem looks something like this. We have a person and an item, and we want a numerical assessment of how well that person goes with that item. We'll call that number there compatibility. It could be either 0, 1, indicating that they go together, or it could be a number indicating how much the person would enjoy the item. It could represent how likely the person would be to buy the item, or how much time the person would spend interacting with the item. If the computer can predict the compatibility score of a person and an item, however assessed, it can rank order all the items for a person and present the most compatible ones for consideration. Different recommendation problems differ based on what kind of information there is about the person and what kind of information there is about the item. In one version of the problem, each person and each item are associated with a feature vector. The recommendation system can then predict the degree to which two are compatible by the similarity of those vectors. This version of the problem is unsupervised in that the recommender has no explicitly labeled data about compatibility. There's just an assumption that the more similar the features are between the person and the item, the more compatible they are. Some news story recommendation systems work this way, based purely on similarities. Each article is tagged by editors with keywords like pop music or sports or local politics that describe what they're about. And the users select descriptors for themselves from the same set. Articles where the keywords match a user's descriptors are judged as compatible. By contrast, in the supervised version, there are explicit compatibility judgments between people and items. That's the structure that's used in systems like online shops or video services that ask you to rate what you just bought or watched. The recommendation system then needs to generalize from these examples to identify additional compatible pairs of people and items, even though no compatibility judgment is available for these other pairs. This version of the problem is supervised in that a sample of compatibility judgments is available for training the system. A common variant of supervised recommendation is a recommendation system that can actively solicit compatibility judgments to gain new information for prediction. For example, it can recommend an item and then wait to find out how compatible the person and item actually are. This new information could be based on the person's direct judgment or an indirect measure, like whether the person takes the recommendation. One difference between an active and a passive version of supervised learning is that an active system might seek information by recommending an item that is not its best guess for the most compatible item. Instead, it might calculate that knowing a particular person-item compatibility value will better situate the algorithm for making future judgments more accurately. As a result, it can get up to speed more quickly for new items or new people. The strategic, sequential nature of this decision makes the active version closely related to reinforcement learning. All three of these approaches to recommendation, unsupervised, supervised, and reinforcement learning, are behind popular user-facing information technologies and remain an important and active area of research. Let's delve into these three main classes of recommendation problems, starting with unsupervised approaches. The big insight of the Toronto paper matching system is that the best information about a reviewer's expertise is the published work of that reviewer. The system asks each reviewer to provide pointers to a bunch of representative papers that the reviewer has authored. These papers are then processed to create a bag of words feature vector for the reviewer, capturing that reviewer's expertise. The Toronto paper matching system represents a reviewer in the vector space model by pooling the words in the reviewer's representative published papers. Of course, submitted papers can also be represented in this same space. There, we can compare the reviewer's vector and the paper's vector to get a pretty good indication of compatibility. The comparison can be done using the dot product or the normalized dot product, the cosine, as these measures have been shown to be very effective at capturing a sense of overall similarity. So that's the main idea. The system recommends papers to a reviewer if those papers have high similarity to those written by the reviewer. Many conferences just use unsupervised rankings. That's already a helpful tool for focusing reviewers on the papers they are most likely to be able to review knowledgeably. But the Toronto paper matching system incorporates supervised learning as well, since reviewers are allowed to add explicit compatibility judgments to the calculation. To see how that works, let's start with a really easy case. Each person and each item are represented by vectors. For a large subset of people and items, we also have compatibility judgments. A combination of a person vector and an item vector have an associated compatibility. For a new pairing, we have the person vector and the item vector, and we need to predict compatibility. So we have a supervised learning problem. But there's a cool alternative that's possible when we're doing recommendations. Let's say we're making recommendations and we already have many compatibility scores for each person and each item, although not for all possible pairings. The data is arranged differently now. Each person is a row, and each item is a column in a matrix. A cell of the matrix is filled in with the known compatibility score for the corresponding combination of person and item. If the compatibility score is unknown, then it's not filled in. The pattern of compatibilities conveys a lot of information. In fact, there's so much information there that a recommendation system can make good recommendations even without using feature vectors to represent each person and item. Let me say that again. Given this kind of compatibility information, it is not necessary to come up with feature vectors. In a sense, the pattern of compatibility scores becomes a kind of feature representation on its own. Learning compatibility scores from this kind of input data is known in the field as collaborative filtering. Essentially, the preferences expressed by other users can help identify items that you are unlikely to want. The filtering out of unwanted items is being accomplished collaboratively. One of the most influential and large-scale experiments on collaborative filtering was a competition known as the Netflix Prize, which took place from 2006 to 2009. Netflix wanted help to improve their existing recommendation system, Cinematch. They offered $1 million for the first team that could produce a 10% improvement over Cinematch's recommendations. The folks at Netflix already had a pretty good handle on machine learning, and it shows in the way they structured the competition. First, Netflix provided a training dataset of over 100 million ratings given by 500,000 users to around 18,000 movies. Compatibility scores were given on a 1 to 5 star scale. The title and year of release of each of the movies was provided separately, and competitors had the option of looking up additional information about the movies. The users were identified only by a numeric ID, and Netflix tinkered a bit with their ratings to try to make it hard to figure out who users actually were. As it turns out, the attempt to conceal user identity was not very successful. An independent group showed that they could identify some of the users by name based on their ratings and other public information. In the end, a privacy lawsuit prevented Netflix from running another public competition with user data. Anyway, to evaluate a contestant's proposed recommender formula, Netflix created a list of 3 million user movie combinations. Contestants needed to make a compatibility prediction on these combinations and send them to Netflix for scoring. The score on half of these queries was used by Netflix for their official internal standings. That's a testing set. The score on the other half were used to let competitors estimate how well they were doing. It's a validation set. Netflix used root mean squared error for scoring. That is, the contestant provided a predicted compatibility score for a person-movie combination. Let's say the prediction was 3.8 stars. Netflix compared this value to the actual rating the person assigned, then squared the difference. If the person assigned a rating of 3, the penalty for that example would be 3.8 minus 3, or 0.8, and squared equals 0.64. If the person assigned a rating of 4, the penalty would only be 4 minus 3.8 squared equals 0.04. So Netflix chose a loss function that encouraged competitors to match the target number of stars as well as possible. They would compute this loss and send it back in aggregate to the contestant who submitted the predictions. Netflix did the accuracy calculations themselves instead of providing testing data to the contestants. There needed to be a solid wall between training and testing to truly assess generalization. And with $1 million on the line, opportunities for cheating needed to be avoided. It was a pretty elegant competition. Teams could download the data, play around with it as much as they wanted, and submit up to one new set of predictions each day in the form of a big text file. By the end of the first year of the competition, over 40,000 teams from 186 countries had registered. There were a few algorithms that teams were drawn to. One was a variant of a nearest neighbor algorithm. If you want to predict a compatibility score for a person, think of all the ratings provided by that person as training data. The movie we want a prediction for is the testing data. But to apply nearest neighbors, we need a way to judge the similarity of movies. How similar is movie I to movie J? Well, each column of the matrix is a vector where the components are compatibility scores. And we have good ways of measuring vector similarity, like dot product or cosine. The tricky part is that the vectors have holes in them where compatibility scores are unknown. So competitors just ignored components where the data was missing for either of the movies being compared. That ends up working pretty well. But in the search for methods that work well for the problem, teams discovered that combinations of methods tended to outperform the individual methods, even the strongest ones. The winner of the first Progress Prize, a year into the competition, achieved an 8.43% improvement using an ensemble of a whopping 107 algorithms. As final prize deadlines neared, teams that were not in the first place position approached each other to form supergroups so they could merge their algorithms. The final winner was an even bigger ensemble that pulled together hundreds of algorithms where the predictions of individual algorithms were mixed together with weights trained by linear regression. Even minor factors such as the day of the week the movie was reviewed and how many movies were reviewed all at once turned out to give ensembles slight advantages over simpler methods. In the end, the 3-year race to the finish line was won by a 20-minute difference in submission time. That's like the winner of a foot race marathon being decided by 0.09 of a second. Very exciting. As it turns out, Netflix never implemented the prize-winning solution. Instead, they reported cherry-picking just 2 algorithms that together accounted for most of the improvement. One was a technique for reducing the dimensionality of the problem called singular value decomposition. The other was an early precursor to deep neural networks called restricted Boltzmann machines. In any case, none of this work was designed to address another key problem that has to be solved to deploy these systems in practice. It's called the cold start problem. And that problem brings us to our third approach to recommendation, one closely tied to reinforcement learning. The question is, how should a recommendation system balance making recommendations that it thinks are good for that person against exploratory recommendations aimed at discovering something important about the person's overall preferences? This problem comes up often outside of recommendation. It was first studied in the context of medical treatment allocation. If you're testing 2 treatments for a disease, how can you learn which is more effective while giving good treatment along the way? The problem is sometimes compared to one faced by a gambler choosing amongst slot machines. Slot machines have the nickname one-armed bandits because they have a single arm that you have to pull and they steal your money. I saw a literal take on this name at the San Francisco airport. It is a slot machine made to look like a one-armed bandit. Anyway, our third method for making recommendations is like a gambler playing slot machines and switching away from those that feel like losers. The problem is called the K-arm bandit, where each arm is a different slot machine the gambler can choose. For our purposes, the arms correspond to items that can be recommended. Here's an example. When Barack Obama was first running for president in 2007, the staff for his website wanted visitors to sign up for a mailing list and donate money to the campaign. His team thought that the design of the webpage might have an impact, so they decided to do an experiment. The experiment involved showing different visitors to the page different combinations of a splashy visual and the message on the sign-up button. They were interested in testing 4 buttons and 6 visuals for a total of 24 combinations. In their experiment, each visitor was randomly assigned to a combination, and they showed 13,000 visitors each combination. So over 300,000 visitors were in the training set, and their click behavior was the feedback. The best performing combination was a picture of the Obama family along with "Learn More" on the sign-up button. The staff estimated that the use of this combination, instead of the one they were planning to use, brought in an additional 3 million signups and an additional $60 million. That's like winning 60 Netflix prizes all at once. This problem setting is commonly called A/B testing because it is often applied to select among 2 choices. Here, we're trying to figure out which of the 24 combinations we should recommend to the average visitor to the site. We can view it as a kind of recommendation problem in the form of a 24-armed bandit. We're filling in the compatibility scores by showing the layouts to people and seeing whether they sign up. In this example, we wait until each layout is seen 13,000 times before deciding to commit to the best combination. This approach to the problem is simple, but it has an important downside. Even if one of the items is clearly worse than the others, this approach still recommends it many times while gathering data. During the learning process, the algorithm doesn't focus in on the most promising item. We say it only explores and never exploits. It's not terrible, but it seems wasteful. At the opposite end of the spectrum, consider an approach that shows people configurations at random until someone signs up. At that point, it switches to the configuration that led to success. This approach explores only until a single person signs up and then only exploits. That might work out okay. The algorithm could get lucky and the first configuration to work might actually be the best one, but there's a good chance it'll latch onto something suboptimal. Assuming the first positive result is the best positive result is risky. So it can work out a lot better if we balance exploration and exploitation. One simple approach to mixing exploration and exploitation is to switch off between these 2 modes probabilistically. Each time a decision is made, this approach says, with high probability, be greedy and select the arm that appears to be the best, that is exploit, but with low probability, choose an arm at random, explore. The small probability value is referred to by the Greek letter epsilon, which has been used since the early 1800s to refer to small values. This epsilon greedy approach is popular because it can be easily adapted to many different circumstances. However, the epsilon greedy approach doesn't really take into consideration how confident we are that one item is truly better than another. In fact, it ends up overexploiting early on when it has little reason to have a preference, and then overexplores later on after it has built up an accurate estimate. A mixed method that's better at incorporating how uncertainty declines is called the upper confidence bounds approach. It splits its estimate of compatibility into two parts: the average compatibility observed and a confidence interval around this estimate. Then the algorithm greedily selects the item with the largest estimate plus confidence interval. The approach explores when estimates are uncertain and exploits when the item with the best compatibility exceeds the upper bound of the uncertainty of the next highest item's compatibility. To illustrate this idea, imagine we're comparing three layouts. Early in training, the compatibility of the first layout has been estimated to be exactly 7. The second layout is estimated to be anything from 1 to 9, with an average of 5, marked with a blue box. The third layout is estimated to be between 4 and 8, with an average of 6. At this moment, an epsilon greedy approach would select the first layout with high probability because the most likely value for the first layout is larger than the most likely value of the other two layouts. But the upper confidence bound approach would select the second layout. This approach is looking at the upper values of each, and there's still a chance that compatibility for the second layout could be 9, higher than either of the other two. Late in training, it becomes clear that the second layout's compatibility is actually between 4 and 6. The upper confidence bound algorithm will switch to the third layout, and in this case, discover that its compatibility lies at the upper end of its range, making it the best choice. The approach can now exploit by choosing the third layout, even though it's still uncertain about the precise compatibility of the second layout. Let's think about how we can apply what we've seen to another recommendation problem. We're designing a wake-up service that will show a user a news story on a screen in the morning. Each day, there are 5 news stories that can be featured. The user is shown one and can click like or dislike depending on whether the story was worth seeing. Each news story can be represented as a bag of words feature vector. News stories never repeat, so this recommendation system will have to generalize to be effective. In the machine learning community, this problem is known as a contextual bandit problem because it must use its judgments based on vectors that describe the context of people or items or both. Let's try out some algorithms for this problem. For starters, I made some data consisting of a few thousand titles of academic papers. The dataset has one paper title per line. Half of the papers are machine learning papers from the ICML conference. The other half are robotics papers from the IROS conference. I mixed them all together and then unfairly tagged all machine learning papers as interesting, 1, and all of the robotics papers not interesting, 0. We'll read in the file cb.txt consisting of the titles of the papers, and we'll read in the file vocab2.txt listing the words in those titles. I wrote some auxiliary code to read in the text files containing all the titles. Read vocab reads the vocabulary file and assigns a numeric identifier to each word type. Tokenize turns the titles into numeric vectors based on the words they contain. GetDat reads in the collection of titles cb.txt. It uses tokenize to convert the titles into numeric vectors suitable for machine learning training. Now that we've read in the data, we're going to simulate 200 days of interactions. We'll call it incremental recommendation simulation. It's like a game. Each day, the chooser sees 5 titles and selects only one of these items to show to the person. Then the person provides feedback, a 0 or a 1. 1 means the person found the item interesting. If the chooser chooses an article the person found interesting, 1 point is added to the score. After that feedback is provided, the title and the judgment are added to a training set. If the chooser just guesses at random every day, the score will be around 100. If the chooser chooses right every day, it would get a score of 200. But initially, the chooser has no idea what the person likes. It must do some amount of exploration before it's able to start choosing correctly. Now we can evaluate different learning approaches to the iterative recommendation simulation. As a first strategy, we'll ignore exploration. We'll focus on exploitation by training a naive Bayes classifier to assess each of the 5 incoming titles, and it will choose the most promising one to show to the person. We'll have the chooser guess randomly for alpha days. Then it will use the gathered examples to train the classifier. For the remaining days, it will use the classifier to decide what to choose. Let's see what happens with a range of alphas from 10 days to just under 200 days in steps of 5 days. For alpha equals 195, performance is indistinguishable from random because the chooser spends almost all 200 days collecting data. It's exploring and learning a really good classifier, but it scarcely ever uses what it knows. For low values of alpha, like 25 or fewer, the chooser collects some data, then it uses that data to make decisions. The score isn't too bad. But there's a kind of happy zone of alpha from maybe 25 to 75 days where the trade-off between exploration and exploitation is even better. The strategy scores around 150 to 160 in this zone. So far, we've been training once and using the results throughout. But we can get even more improvement if we retrain with every new example that comes in. To wisely trade off exploration and exploitation, we need a way to tell how confident the classifier is in its assessments. The naive Bayes algorithm has a built-in parameter that can help. When a naive Bayes model learns, it tallies up counts on each feature for each of the classes. In principle, this initial count should be 0, but when there's only a small amount of data, the model can end up overfitting and behaving erratically. So we can use a non-zero value to start the count. This approach is known as Laplace smoothing, and it makes the algorithm more robust when trained with small amounts of data. Setting the smoothing parameter to a very large value means that the algorithm needs to see a lot of examples before it can distinguish the different classes. In effect, a large smoothing parameter forces more exploration. Conversely, using a smaller smoothing value lets the algorithm be more reactive to the data it has seen, resulting in much faster exploitation. We will retrain our naive Bayes classifier after every interaction, but we'll experiment with different values of the smoothing parameter, also named alpha. The chosen item returned is just the one our classifier thinks is most likely to be interesting. The smoothing parameter values I tested ranged from 0.0005 to 1.0. So let's plot the smoothing parameter against the score to see what values led to the best outcomes. The score of the strategy for a maximum smoothing value of 1 is around 159. That's where performance topped out with the explore then exploit method shown earlier. However, bringing the smoothing parameter down to 0.1 or 0.2 results in scores improving from 159 to around 164. That corresponds to 5 additional days satisfied out of the 200. With even lower values of the smoothing parameter, the strategy tends to underexplore, exploiting too early and lowering its score as a result. Adopting a smart strategy and the right amount of exploration can significantly improve the strength of recommendations a system can make. Learning-based recommendation systems have been a lifesaver to people who would otherwise be swamped by information. The case of recommending papers to reviewers is an example where the incentives are mostly aligned. Authors want their papers to be read by reviewers who are knowledgeable and interested, while reviewers want to read interesting papers. But machine learning systems are deployed to recommend all sorts of items to people, and sometimes providers face strong incentives to game the system to get their items recommended. On an ad-supported video delivery platform, the situation is more like the Wild West. Video producers get paid for views even if the viewers are unhappy or even if they are harmed in the long run. Big tech companies like Google would prefer to limit incentives for unwanted behavior that threatens the value or reputation of their platforms, but it's an arms race. In 2019, I attended a workshop at Google to talk about next-generation recommendation systems. The academic attendees were brimming with exciting ideas to try, but the battle-weary Google engineers' attitudes were much more grim. They pointed out how most of the new ideas being discussed are themselves vulnerable to manipulation and are therefore non-starters. It's not easy to make systems that learn and improve, but at the same time avoid latching on to misleading inputs from unscrupulous participants. One cool suggestion that came out of the workshop was the idea of moving away from implicit measures of user interest like clicks or viewing time towards systems that let the users explain why they like or do not like particular content. I hope future recommendation systems will incorporate options for users to explain their preferences, so systems can tune their behavior accordingly. For example, some existing sites let people write reviews. What if the recommender systems read the reviews to understand the justifications for the user's rating, and then recommended items based directly on justifications? Justification-based recommendation could distinguish between providers who are gaming the system and those who are producing items that people actually want. That could make the internet healthier for all of us. How can a machine improve its strategy for playing a game? When Arthur Samuels popularized the term machine learning back in 1959, he was describing a method that let a checker-playing program he created improve by playing against itself. Since then, machine learning programs have been designed that learn to play well a variety of high-profile games. Reinforcement learning is the problem of learning behavior rules from evaluative feedback, like what you get for winning or losing a game. The game of Othello is a great place to dive in. It's a famously easy game to learn, to play, but the strategy space is rich and interesting. Like checkers, chess, or Go, Othello is played on a grid-shaped board in full view of both players. They take turns placing tokens on the board. Tokens can change allegiance during the game, and the player who controls the most tokens at the end wins. We can visualize gameplay in Othello and many similar games in the form of a tree. Trees come up all over the place in computer science, like in decision trees. The root of this game tree is the initial board. We can refer to board positions generically as the game state. We'll build up this game tree with game states iteratively. Because it represents all the possible ways the game can be played, we call it the game tree. Othello games always start with 2 black and 2 white on the board. The only moves that are legal involve surrounding at least one of the opponent's pieces from opposite sides, after which the surrounded piece is flipped to the opposite color. From the initial game state, there are exactly 4 legal moves that black can make. On our game tree, we can draw a line for each of black's moves that take us to a new game state. Because of symmetries in the board, each of the 4 possible game states provides exactly 3 legal moves for white. In the form of a game tree, we have something that looks like this. The set of boards and the paths to reach them are expanding. Now, for the first time in the game, symmetry is broken. Different choices for black's second move lead to game states with different numbers of options for white. In some game states, black has 5 possible moves. In others, there are only 4 possibilities for black. Here's what the game tree looks like at this stage. Notice that the game tree is starting to get crowded. And it's only going to get worse. There are 64 squares on the board, and even if players only have 2 choices available on each turn, we're still talking about a game tree with 10 quintillion leaves. But let's ignore that little bit of intractability for just a moment. Every game of Othello ends, no matter how players play. In addition, every final game state can be categorized as a win, loss, or draw for the starting player. So if we could magically reach the very bottom of the game tree, we'd be able to label leaves as a win, loss, or tie for black. Now consider a game state of the game tree where it's black's turn to move. Let's further imagine that we've already determined for all of the children of that game state whether they are a win for black or white or a draw. Here's what the situation looks like. The green square is a game state where black has 4 different moves. The first leads to a win for black, the second and fourth lead to wins for white, and the third leads to a draw. What can we say about the green game state? Since it's black's turn and black wants to win, we can assert that black will choose the first action, leading to a game state where black wins the game. So it's not much of a stretch to say that the green game state is one that black will win. Let's color it black to reflect that idea. That's really useful. It means we can propagate up the game tree information about whether each game state is a win, loss, or tie. In fact, we can color all the game states of the game tree as long as we know how to propagate information for all possibilities. So far, we figured out that if a position where black moves can reach a position that is a win for black, well, then that position is also a win for black. But what if a position can only reach draws and wins for white? Well, if there's a way black can draw, that's preferable to losing. So black should choose to win or else draw. Otherwise, black has no choice but to lose. So here's something clever we can do. Instead of making rules with colors, let's use numbers. We assign a win for black a +1 value, a draw a 0 value, and a win for white a -1 value. That means we can express our color propagation rule as a simple mathematical formula. The value of a game state where black moves is the max of the values of its children. That rule covers all possible cases. It also makes it very simple to specify what happens in a game state where white moves. There, the value of the game state is the min of the values of its children. Since the rules of the game tell us how to label the leaves of the tree with either +1, 0, or -1, and we can calculate mins and maxes up the tree as needed, we can, in principle, label all of the game states in the game tree with these values. Okay, well, why is that useful? Because it encodes the optimal strategy for black. When it's your turn, take whichever move leads to the highest value game state. Simple as that. Alas, we can't really build a program like that to play Othello. There are smaller, simpler games like tic-tac-toe and Nim where this approach works perfectly, but for Othello the game tree is just too big. But despair not. There is a general recipe for playing games like Othello that has turned out to be super effective. What we're going to do is this. Each time it's our turn, we're going to run an algorithm for selecting a good move from the current board. To do its job, the algorithm needs two things. One is an approximation of the optimal labeling of game states as win, draw, loss. That is +1, 0, -1. We'll call this program the evaluation function. Second is a rule for choosing which moves we want the program to consider in its search for a good move. We'll call that our sampling policy. If the big dark green triangle is the full game tree that's too big to search for Othello, our evaluation function and sampling policy let us create a miniature version of the game tree for evaluating a game state. We'll use the sampling policy to trace out a piece of the game tree. We use the evaluation function to assign values to the leaves of that mini tree. Then we use the rules we've been discussing to propagate the leaf values up to the root of the mini tree so an action can be chosen. We'll make our move in the game based on the values that we get from this calculation. Okay, let's apply this idea to Othello. For simplicity, we'll use a sampling policy that chooses all possible moves up to a depth of a dozen or so. But how will we evaluate the game states we reach at that point? Starting in 1993 or so, Michael Burrow created an Othello playing program that followed this game tree approach. Earlier efforts used human design evaluation functions. A key innovation in Burrow's program is that he used a machine learning approach to create the evaluation function. Specifically, Burrow defined a set of Othello-relevant features of boards. They included information about how many available moves there are, who has more tokens, whether the player controls important parts of the board like the corners, etc. He collected expert games and also simulated lots of examples of game states along with whether those game states led to a win, loss, or draw for black. He had around 3 million game states, which was a lot of data back in the 1990s. He then trained a classifier to predict the likelihood that black would win. He used our friend logistic regression to capture this mapping. He named his program Logistello, a combination of logistic regression and Othello. After several years of development and refinement, Logistello became the first program to beat the reigning human champion in Othello. The match took place just 3 months after the much more widely publicized Deep Blue Kasparov match, in which a computer beat the reigning human champion in chess. In fact, Deep Blue used the same game tree strategy template we've been talking about. Deep Blue's sampling policy went about 21 moves down the tree, considering all possible moves at each level. Unlike the less famous Othello example, Deep Blue's evaluation function was built by people, no machine learning there. But even so, machine learning did play a pivotal role in Deep Blue's eventual success. Here's how. Jerry Tesoro is a machine learning researcher at IBM. He worked on Deep Blue and developed a novel machine learning technique for learning move preferences from human examples. His technique was used in Deep Blue in the narrow area of king safety evaluation. Kasparov and Deep Blue had their first match in 1996, which Kasparov had won. But during a rematch in 1997, this part of the evaluation function made a critical difference in one important game state in Game 2. It assigned a higher value to the game state than a typical chess program would have, resulting in a nuanced move that surprised Kasparov. This surprise may well have contributed to psyching out Kasparov and changing the momentum of the match in favor of the computer. Kasparov lost that game, managed 3 draws, then lost the final game. Sorry, humanity. In the generic game tree approach I described, there are a few ways machine learning can contribute. Lagistello took a supervised approach to learning the evaluation function. Specifically, in its training data, it used pairs of game states and their final outcomes. In backgammon, Jerry Tesoro tried an even more interesting machine learning approach. Instead of gathering expert training data and training a learner to mimic experts, he framed backgammon as a reinforcement learning problem. He had his program play against itself. It would make moves using its current estimate of the evaluation function, then it would update its predictions using an approach to reinforcement learning called temporal difference learning. The supervised approach says we need to pair game state with its outcome given optimal play. The temporal difference version of learning says we don't know optimal play, but we can use the insight we discussed earlier. Specifically, the evaluation of a game state where the player has a choice is the maximum of the evaluation of the game states that can be reached in one move. We might not yet have a good estimate for those game states, but we're going to keep doing updates and make the game tree values more consistent from one step of the game to the next. We don't need expert examples. We just need lots of chances to make things match up. This TD gammon approach ends up playing very strong backgammon. Tesoro's results brought reinforcement learning and temporal difference learning to many people's attention back in 1992. The game of poker is quite different. Poker players make decisions under incomplete information, not knowing what their opponents see in their hands. You can build a game tree for poker, but you can't propagate values up the tree the way we discussed for Othello. The reason is that there are game states in the game tree where a player has the same information and must therefore behave identically. Here's a tiny example to give you the idea. In the movie The Princess Bride, 2 characters engage in a deadly battle of wits. One, the man in black, adds poison to one of 2 goblets of wine secretly. He then places one of the goblets in front of his opponent and the other in front of himself. The opponent, Vizzini, must then choose one of the goblets. At that point, the 2 men drink and one dies. It's a comedy. Here's the game tree representation of this game. The man in black chooses first and either poisons his own goblet or Vizzini's. Then Vizzini chooses to either drink his own goblet or the one in front of the man in black. If we use the labeling rules described earlier to propagate information up the tree, we find that the game is a win for Vizzini. In particular, Vizzini wins by drinking from whichever goblet has wine and not poison. Simple, right? Not remotely! No. That's because the game tree fails to record an important part of the game, which is that the man in black's decision was made privately. Vizzini can't use this information to decide which action to take. He must commit to taking the same action in both of those 2 game tree states. There's no clear way to constrain the choices using the standard game tree algorithm. Marty Zienkiewicz and colleagues came up with an approach that can learn to play quite well in games like this one. The basic idea is that there's a probabilistic strategy for each of the sets that contain game states that players can't distinguish due to partial information. So for this game, we'd have a set of choices for the man in black at the top node and a set of choices for Vizzini for the pair of middle nodes. Here's where machine learning comes in. The players can compute what's called counterfactual regret. Roughly speaking, it's a measure of how disappointed they are for not playing each of their possible moves in each possible circumstance. A player can simulate playing the game repeatedly in his mind. A regret minimization algorithm chooses actions proportional to their regret. The more you wish you had done something, the more likely you'll be to do it next time. If we update the strategies and repeat the process, the average strategies of the two players will be regret minimizing. That is, they will find a way to behave that is the best possible, considering that the opponent is trying to do the same. Strategies for the two players such that neither can unilaterally improve his chance of winning is what economists call a Nash equilibrium, after mathematician John Nash. The idea of counterfactual regret minimization can be thought of as learning from imagined self-play, and it is at the heart of several breakthroughs in computer poker play. In 2017, a team from the University of Alberta used counterfactual regret minimization to derive a near-perfect solution to a popular two-player version of poker called Heads-Up Limit Texas Hold'em. In 2019, the system Pluribus from Carnegie Mellon and Facebook used a version of counterfactual regret minimization to address the tournament version of the game, Texas Hold'em with no limit and 6 players. In an exhibition match with 12 poker professionals, Pluribus achieved a decisive victory. But even in poker, or blackjack, we at least know what the rules are. In 2015, DeepMind announced that they had created a reinforcement learning algorithm that could learn to play any of a suite of Atari video games. By some measures, the program's performance was on par with a human video game expert. One of several things that makes this result so exciting, so different from earlier results like what was achieved in chess and Othello, is that video games don't have a well-defined set of rules the way that board games do. Part of the fun of many video games is learning how things work and learning how to control the characters so they do what you want. And when the rules are not known in advance, the whole game tree idea goes out the window. Whereas an Othello player has to learn about how to sequence actions to bring about a winning position, a video game player also has to learn how things work. The DeepMind group adapted a reinforcement learning algorithm called Q-learning to solve this problem. Q-learning is a variant of temporal difference learning. DeepMind called their full algorithm Deep Q Network, or DQN, because it combines Q-learning with deep networks. The main innovation of Q-learning is that values are learned for the moves in the game tree instead of for game states. That makes a huge difference. Game tree search requires that we can enumerate the game states reachable from the current game state S. Learning moves avoids this difficulty. In fact, if we've learned values for all the moves, then move selection is easy. Just take the move with the highest value. Since the identity of the resulting game state is not needed, this approach can be used just as easily in video games as it can be in board games. In addition to Atari games, variants of this approach have been used to play at the level of top human players on big-name multiplayer online battle games such as Defense of the Ancients 2, known as Dota 2, and real-time strategy games such as StarCraft 2. The deep learning methods that have been used in these games require hundreds or thousands of powerful computers to reach expert performance. But we can use a similar approach to learn to play a simple but real-world game, blackjack. The basic idea of the Q-learning approach is as follows. 1. Let QSM be a function that maps a game state S and an action M to a value. The value represents the probability we'll win from game state S if we make move M and then take optimal moves after that. These values can be initially random. 2. Then each time the learner sees the game state S leads to a game state S prime, when move M is taken, it uses its estimate of the value of the best move to take from S prime to update QSM. We're going to use a decision tree to represent Q, and we'll retrain it periodically as more data comes in. Let's implement this idea for blackjack. Blackjack and a bunch of other reinforcement learning environments are defined in a package called GYM from OpenAI. You get access to these environments by simply telling Python to import GYM and running gym.make on one of the environments. We're going to start with an evaluation function, initially all zeros. Then, for each of 5 epochs, we're going to play n equals 100,000 games of blackjack in each epoch. At the end of each epoch, we'll retrain our evaluation function. Epochs and n are free parameters, and their choices matter. Playing fewer games per epoch means we'll more quickly proceed to using the new experience we've gained. I picked 100,000 to make sure rare but important events would be in the data. But smaller numbers would perform well here too. Another important parameter is epsilon. At each move in the game, we'll take whichever action has the highest Q value, but just to make sure we get a chance to see how other moves work, we'll choose a random move epsilon equals 10% of the time. Epsilon strikes a trade-off between exploring and exploiting, just like we saw in Lesson 12 about recommendation. In each epoch, we'll gather up a set of training examples consisting of the current game state in DAT and an improved estimate of its value from the Q update equation in lab. We'll also count the number of games we win just to see if we're making progress. For each of n games, we start off with an observation of the initial game state. In blackjack, that comes from dealing 1 card to the dealer and 2 to the player. Until the game is over, we ask our learner to pick an action. We add the current game state and the current action to our training data. Then we take a step in the environment following the selected action. In blackjack, there are 2 actions, hit and stay. What's our estimate of the value in the game state we just left under the influence of the selected action? Well, if the game is ended, we can use the value of the final board as the target. Like if we're holding a 20 and we stand pat and then the dealer busts, we win. The combination of 20 and stay should produce a positive 1. If the game hasn't ended, we need a special case if it's the first time that we're playing. We'll just guess 0 for those games. But if we've played and learned before, we can use the learned evaluation function. We ask our classifier what it predicts from the current board combined with both of the 2 possible actions. We would generally take whichever has the higher value, so value is the max of these 2 predictions. We keep track of the number of times the game ends in a win, and after all the games in this epoch are over, we train our predictor with the newly collected data and do it all over again. The learner is a decision tree regressor. It's just like the decision tree classifier we've used before, but it outputs a number instead of a class. The number in this case is the prediction of the game outcome, something between -1 and 1. Here, we bound the number of leaf nodes at 6. That's roughly the largest size possible before I found the trees too hard to read. Bigger trees allow for more precision in representing values, and I'd recommend using a number like 20 or 50 if you want to get a really good strategy. The big piece we haven't talked about yet is how the player should choose actions while learning. If we haven't trained our predictor, we can't use it to look ahead. In this situation, we'll just take a random action. Otherwise, we can ask for the value for each of the 2 actions in the current board. If action 1 leads to a higher prediction than action 0, we'll choose action 1. Epsilon fraction of the time, we choose a random action just to see what it does. With the code queued up and ready to go, let's see what happens. First of all, we can see that the first round leads to about 28% wins. That's the win rate in this version of blackjack for a random player. But the win rate jumps up to 41% in the very next round. Falls off a bit to 38% for subsequent 3 rounds. In fact, that result is pretty consistent. Since we're learning a decision tree, we can peer inside to see what kinds of predictions it learned. The tree first tests if the player has 18 or less. If so, it checks if the dealer is showing an ace. If so, it predicts a highly likely loss, a value of -0.719. If the dealer doesn't have an ace, it still predicts a loss, but only -0.211. On the other hand, if the dealer has 8 or more, it predicts an intermediate level of loss, -0.513. Interestingly, these values don't depend on the action the player selected, which isn't really a perfect prediction, but maybe it's not terrible. If you have 18 or less, you are probably going to lose. On the right side of the tree are the predictions if the player is holding 19, 20, or 21. In that case, it matters what action the player takes. If it's action 1, hit, the player will likely lose. The predicted value is -0.537. But if the player stays, the player will likely win with a 19. the prediction is 0.263. But if the player has 20 or 21, winning is even more probable. The prediction is 0.674. I don't think you can do any better than 41% in this game. Interestingly, that's what the algorithm found in Epoch 2. I think the reason the algorithm found that solution so quickly is that blackjack is a relatively shallow game. There are not many decisions per game, so a little learning is enough. Other games would require a lot more epochs. Why does the performance get worse after the first epoch? I'm not quite sure. It could have to do with the fact that the decision tree is only approximately accurate due to the limit on the number of leaves. Allowing bigger trees does help the system learn better policies. Earlier, we talked about learning in game tree search and pointed out two places learning can help. The first is in the prediction of good actions to pursue. The second is in making good value predictions. Research has found that in some games, a good sampling policy is easier to learn, and in others, a good evaluation function is easier to learn. In games like chess, evaluation functions work well. The number and identity of the pieces left on the board tell you a lot about who is winning. As a result, there's no real reason to limit the actions to evaluate. When making decisions, typical algorithms in these games search wide and shallow. That is, they consider all possible actions, but use their evaluation functions to deal with the fact that we can't search widely and still reach the end of the game. For many years, this approach was the only game in town, but the community later realized that there is a classic board game that just isn't amenable to this approach. The game is Go, and it seemed as though it just isn't possible to learn an evaluation function for Go that's good enough to be used in this kind of search. In 2006, machine learning researchers showed an alternative with a great deal of promise in Go. The idea was to search narrow and deep. That is, it's better to evaluate a board in Go by searching to the end of the game where the outcome can be computed accurately. But it matters less which actions you choose to get there. In fact, even random actions can be quite informative, guided by a kind of bandit-based search that balances exploration for learning and exploitation for focusing on promising lines of play. Maybe random actions work for Go because the pieces don't move around, and unlike in Othello, captured pieces are removed from the board, not flipped to the opposite color. So in Go, it's possible to assess what territory is controlled now by looking to see what happens later. In any case, searching narrow and deep led to rapid progress in Go. By 2016, DeepMind showed that they could combine methods for learning a good sampling policy and learning a good evaluation function. For the sampling policy, they trained on human expert games and also on the results of their own program's choices. For evaluation functions, they used a reinforcement learning approach. They called their system AlphaGo. It was the first program to beat a human champion in Go, and a later version beat the #1 ranked Go player in 2017. That same year, they provided a system that could play exceptionally well even without first training on human play. They called that version AlphaGo Zero. Also in 2017, they announced AlphaZero, which was an approach that could learn to play championship-level Go, shogi, or chess with minimal changes. It's a remarkable achievement. There's been amazing progress on using machine learning approaches to play board games like Go. There's also been breakthroughs in using machine learning in partial information games with bluffing, like poker. So you'd think that partial information board games would be a snap. The game Stratego is a great example of such a game. Pieces take their places on the board in a manner that is very reminiscent of chess. But unlike chess, the identity of the pieces is kept a secret. Like poker, players need to bluff and to look for clues to guess which pieces are in play. Unfortunately, the counterfactual regret idea that is key to top poker play doesn't seem to translate so well to this board game scenario. There's just too much hidden information to reason about. As such, computer play of Stratego lags far behind the kinds of results we've been talking about. Some researchers have crossed their fingers and tried to treat Stratego like a video game, where deep networks have been so successful, but the depth of strategy they achieve is still far below good human players. So even in the narrow world of board games, there's still much to learn and much to study. And the real world combines all of these challenges and much, much more. A lot more research will be needed to develop programs that can reason about real-life situations. But next time, we'll look at an important step toward dealing with the real world, the problem of vision and learning how to see. Alan Turing is one of the towering figures in computer science. His name is now attached to one of the central ideas in the theory of computation, the Turing machine. He's also connected with a seminal concept in artificial intelligence, the Turing test. Because he had such a lasting impact, the highest honor in computer science, kind of like our Nobel Prize, is also named for him. It's called the Turing Award, and it has gone to results in computer science from networking to programming languages to cryptography. Awards for machine learning have been scarce, but in 2018, the prize went to 3 researchers for their pioneering work on deep neural networks. I attended the award ceremony, and it was a big moment for a lot of people in machine learning. Given the impact of deep learning, it made a lot of sense to acknowledge these researchers, Yoshua Bengio, Geoffrey Hinton, and Yann LeCun. But what was less obvious was that these 3 researchers, and others, had labored for many years to reach this point. One reason it wasn't obvious was that just a decade earlier, these same 3 researchers went out of their way to obscure the neural aspect of their work. The description of a workshop they helped organize in 2009 focused on the construction of what they called high-level representations and deep architectures with nonlinear processing. By high-level representations, they meant the contents of an image, animals, objects, scenery, as opposed to just things like colors and edges and shapes. Deep architectures with nonlinear processing just means neural networks with many layers. They were hiding the connection to neural networks because neural had become a kind of taboo piece of terminology in machine learning. It had been popular in the 60s and again in the late 80s and early 90s. But the techniques failed to live up to the hype, and the community became disillusioned with anything neural. A few diehards continued to work on neural networks, but it was a niche topic, and work was happening mostly underground. The pivotal moment that helped neural networks climb back into the light was when they revolutionized work in computer vision. Specifically, they vanquished the competition in the ImageNet Large-Scale Visual Recognition Challenge in 2012. ImageNet is a dataset of photos, along with labels of what each photo depicts. The challenge uses a subset of the larger dataset with 1,000 different categories, including types of animals, plants, activities, materials, and human-made objects. In many ways, the ImageNet challenge was a lot like the Netflix challenge we talked about in the lesson on recommendations. A training dataset of approximately 1 million images was released to participants along with a validation set of about 50,000 images and a test set of about 150,000 unlabeled images. Each year, an exhibition was held to reveal which techniques had produced the best performance. Here are the performance figures from the first 5 years of the challenge. On the y-axis is error on the testing set, and the x-axis is the year. As you can see, performance steadily improved over the window of this time. By 2014, the error had dropped to less than a quarter of where it was in 2010. All of these results were produced by machine learning algorithms. The 2010 and 2011 results used sophisticated applications of support vector machines, an approach to creating linear separators we talked about in Lesson 9. In 2012, a newcomer entered the ImageNet competition using the name Supervision. Get it? Supervision and supervision. Anyway, it was a team from the University of Toronto, supervised by Geoff Hinton. Not only did Hinton's supervision improve on the results of the previous 2 years, but the size of the improvement grew substantially. How did supervision do its thing? Neural networks, specifically convolutional neural networks. Roughly speaking, convolutional means that these are neural networks designed to capture local features in images and combine the local features together to identify what the pictures represent. Word spread quickly, and the following years showed substantial improvements as the techniques were refined. In other lessons, we'll talk about how the idea was picked up in other communities. In this lesson, we'll look at the role convolutional networks play in computer vision. We already talked during the lecture about nearest neighbor algorithms about distinguishing instances from one another by voting. If an unknown instance is near some labeled instances, we can have the labeled instances vote, and we can predict the majority label for the unknown instance. For this idea to work as an approach to image classification, we need a notion of nearness between images. Typically, we represent an instance as a numerical vector. The raw information we start with is the array of pixels. We can scale a set of images so they all have the same shape. Let's say that shape is a grid of 224 by 224 little colored rectangles. A color is itself represented by a triple of numbers that encode how much red, how much green, and how much blue there is in that color of the rectangle. So each of these images can be written down as a list of about 150,000 numbers. To measure the similarity between two images, we could take the cosine of their corresponding vectors. That's the normalized dot product, which we talked about in lesson 8. That's fine as far as it goes. That is, we can definitely build a classification system that way. There's not much reason to believe that it would work very well. Two images can have high cosine similarity because they have similar pixel colors in the same locations, and yet clearly be different images. These two images of unrelated objects have a cosine similarity of 0.87, for example, which is close to the perfect score of 1. That's probably because so much of the white background lines up. Conversely, these are both images of dogs, but they have very little overlap at the level of individual pixels. How can we capture images in a form where the similarity of their numeric vectors does a good job of capturing their visual similarity? Let's talk about two approaches to constructing features and how they can be used to recognize images of digits. The first approach uses the raw pixel features we've been talking about. The second is a kind of feature that tries to capture the local spatial relationships between the pixels. These local spatial relationship features will be our jumping off point for understanding convolutional neural networks. We'll see that intelligent combinations of these two approaches can do a really good job of capturing image similarity. The raw feature method we talked about is inherently translation variant. That is, the position of the digit in the image matters a lot. Consider these three digits, 2 4s and a 9. The raw feature space that we've been using thinks that the first and second are highly similar and that the first and third are almost completely dissimilar. Surprising, right? I made the third image by sliding the first one over and up. I created the second image by drawing a 9 on top of the first image. The overlap looks like this. The dark patches are the overlap, so more dark is more similarity. The matching 4s barely touch and are therefore judged as dissimilar. The 9 and 4 share substantial overlaps. Something's not right with these features. Here's another thing that should give us pause. If we take the image and scramble all the pixel positions, reordering them randomly like some kind of sliding tile puzzle, and we do that to all the images, judgments of similarity are completely unaffected. That's weird, right? The features capture nothing about spatial locality in the image and everything about the absolute position in the image of individual dots. That's very different from natural skill at recognition. We recognize a dog or a 4 or a juggling club in an image no matter where it is located. Our recognition is translation invariant. It works the same even as the content slides around. How might we represent these digits with features that are translation invariant, location independent? One idea would be to count up the different kinds of strokes in the image, independent of where they occur. So the 4s would both consist of a short horizontal bar, a tall vertical bar, and a short positive slope bar. No matter how we move the digit around, that description would remain exactly the same. And it would be different from the 9, which consists of a tall vertical bar and a medium-sized circle. Such a representation would satisfy the goal of being translation invariant. But it's still not clear how one would automatically extract such a description from the image itself. So here's a similar idea, but one that is more easily implemented. In MNIST, digits are not made out of strokes, but out of shaded squares. Specifically, a digit exists as a 28 by 28 grid of pixels. Consider a smaller 5 by 5 patch like this. Now I'm using transparent green for +1 and transparent red for -1. You can think of this image as being like a little close-up of a vertical bar. In particular, it is excited by the pixels that line up with the green patch in the middle, and it is inhibited by the two stripes on the ends. This notion of exciting and inhibiting as a way of extracting features was discovered by scientists David Hubel and Torsten Wiesel in their studies of the visual system of mammals. Some cells in visual cortex carry out exactly these kinds of computations to find patches, bars, edges, and various other low-level image features. Here's what we're going to do with this patch. We're going to place it on the top of the image of the 4 in the upper right corner. At each overlapping pixel, you can see that the black part of the image of the 4 blots out whatever is in the patch, leaving black. Wherever there was white in the image of the 4, we can see either transparent green or transparent red. Here we get 6 greens and 3 reds where the patch and the image overlap. We can achieve a similar effect by multiplying the values of the corresponding pixels. Black is 0 and green is +1, so the squares where the two colors overlap are worth +1 times 0, or 0. White is 1 and red is -1, so the squares where those two colors overlap are worth a value of 1 times -1, or -1. Now we will sum up all of these products. In this case, we've got 6 ones and 3 -1s for a total of 3. Finally, we'll say that the patch matches the image at this position if the total is more than 10 out of a possible 25. So in this case, there's no match. Is there some place we can put the patch so that it will match? How about lining it up with the horizontal bar of the 4? Now we have 14.5 cells that overlap with green and none that overlap with red for a total of 14.5. That's more than 10, so we have a match. How about the horizontal bar of the 4? Now we have 9 greens and 6 reds for a total of 3. That's way under the threshold of 10, so no match. Basically, this patch is a little recognizer for vertical bars with a width of 3. If we try the patch at every position in the image, we can get a sense of how much of the image is made up of vertical bars with a width of 3. It doesn't tell us where they are, just tells us that they're out there. Other patch patterns can detect other visual features like rounded edges, diagonal bars, and more. The operation of scanning a patch over an entire image to see what matches we get is known as convolution. It's not that it's convoluted in the sense of being complex. It's because the word convolve means roll together, and we're rolling the patch all over the image to count up matches. Using convolutional patches, we can encode an image like our 4 in terms of the number of matches of each of a set of patches. Each patch becomes a feature in a feature-based representation of the image. As I mentioned before, we get a representation that is translation invariant, but one where we lose a sense of which specific pixels are on or off. Really what we want are features that capture both position and spatial context. If we set up our convolutional filter correctly, we can learn the parameters that define the filter and ultimately pick filters that are tuned to the problems at hand. The neural network architecture that won the ImageNet Challenge in 2014 is called VGG16. Here's a table summarizing its architecture. It's a neural network arranged in 16 trainable layers. That's why it's VGG16. This architecture is the first deep network design we're looking at. Notice that each layer has a particular arrangement. The layers are listed from the input at the top to the output at the bottom. Let's start with the input. Its size is 224 by 224 by 3. The 3 comes from the fact that there are 3 color channels for each of the 224 by 224 image positions. The very first layer that processes the input has a size of 224 by 224 by 64 units. It's a layer of convolutional filters, 64 of them in this case. The convolutional patches themselves are 3 by 3. These parameter settings were chosen by the network designers. VGG16 follows one convolutional layer like this immediately with a second one. The stride of 1 refers to the idea that the convolutions are applied at adjacent pixels in the image with no skips. The activation function for these units is ReLU. They implement linear functions except with a kink defining a threshold minimum value at 0. The next layer of the network is something new. It's called a max pooling layer. It has no trainable weights, so we're not going to count it as a layer in the architecture. Instead, it takes a 3x3 patch of outputs of the previous convolutions and just returns the highest activation in those 9 units. It does so with a stride of 2, so these 3x3 windows are only barely overlapping. The idea of a max pooling layer is that if a convolutional unit discovers something exciting, hey, there's a corner here, we can enhance this information while decreasing the overall size of the layer. Because it uses a stride of 2, the total number of units at the next layer now has 224 divided by 2, while the number of learned features stays the same at 64. So there are 112 by 112 by 64 units. Note that the information is still arranged as a kind of image. It's lower resolution, and there are 64 channels corresponding to the 64 different kinds of convolutional units from the previous layer. The basic structure of a set of convolutional layers thinned out by a max pooling layer repeats 5 times in this architecture. Each time we have a kind of smaller resolution image, but more and more channels corresponding to the kinds of features the network decides to pick out. Finally, the last few layers of the architecture are fully connected, meaning that all the units from the previous layer have weights connecting them to all of the units of the current layer. The explicit spatial information is gone now, and the network is trying to recognize high-level properties of the entire image. The final layer has 1 unit for each of the 1,000 ImageNet classes. The activation is softmax, which means that the activations are forced to sum to 1 across all those 1,000 units, causing them to act like probabilities or confidence values in the different classes. Why this particular arrangement of layers? To be honest, there are lots of different arrangements that have been proposed, and many do good and useful things. I picked this one for several reasons. It did well in one of the ImageNet challenges. It also illustrates many of the architectural ideas that are in use in other networks, convolutions, max pooling, and fully connected layers. In addition, it's freely available for download. It also has been demonstrated to have a nice property whereby the last few layers tend to capture somewhat generic properties of images that can be used for recognizing more than just the 1,000 classes in ImageNet. In fact, that's one of the remarkable things about deep networks that has helped propel them to wide use. They tend to learn computations that solve the task they are given, which is great, but they also do a good job of learning new feature representations for their inputs that can be useful even beyond the specific task they were trained for. I want to talk you through the kinds of image features captured by VGG16. Layer 1 is the visual features learned in a convolutional network close to the input. Edges, color patches, and bars are the types of features selected at this top level. At a deeper layer, there are filters that are sensitive to bits of shape and texture. Some filters might be excited by stripes, others by concentric circles, others by scaly patterns and bumpy textures. Deeper still, filters are reacting to object parts, smooth patches of surfaces, corners of objects, torsos of people, bumpers of cars. The deepest layers include filters that capture objects and their parts in context, items in water, legs on ground, faces on dogs, wheels on grass. The filters in the deepest layers also seem to become somewhat color-specific, with filters preferring patches with red items, say, while others might prefer brown or blue backgrounds. By creating a rich vocabulary of image filters, the convolutional network becomes ideally suited for categorizing any of a large set of possible object classes. In a sense, it's not shocking that the network would decompose images into components in this way. After all, what alternative is there? But it's still exciting to see this kind of analysis being done so automatically and in a way that can generalize to new situations. Another exciting thing about deep neural networks is that the researchers designing them have produced Python libraries that make it really easy to specify and train the networks. Here's an example of code from a library called Keras. It defines the VGG16 network we were just talking about. There are a few really cool things about this code. First, it lets you specify the architecture layer by layer, just like the table. The lines of code match up perfectly to the high-level description. Second, let's take a minute to think about what happens under the hood. These statements are defining layers that are actually building up an explicit representation of a huge parameterized function, a program. And the convolutional filters in this program act like subroutines of their own. When it comes time to train this function by way of gradient descent, it's necessary to take its derivative. And that's something you can't really do on code in general. But these functions are constructing the network not just functionally, but also symbolically, and that makes it possible for the gradient to be computed behind the scenes. When we run the function, it shows us that the whole network consists of 138 million trainable weights. Given its size, VGG16 takes weeks to train, even using heaps of dedicated, specialized, high-performance graphical processing units. That's another thing that's cool about Keras and other deep learning packages. They're optimized to take advantage of fast hardware. Of course, if you don't have that hardware, it's not much of an advantage. But all is not lost. VGG16 was trained to recognize the 1,000 ImageNet categories that include types of animals, plants, human-made objects, geological formations, and more. We have access to a trained version of VGG16 that we can use to recognize objects in any of these categories. But even more importantly, VGG16's learned internal feature representation can be used to build recognizers for new objects without having to train it from scratch. We can generalize beyond the 1,000 classes that the original competition was built around and learn to recognize categories of objects that they didn't even think to include. Fidget spinners, say, or Tesla cars. Or household abrasion tools. Yeah, let's do that last one. If we want robots to help us around the house, they need to be able to distinguish the different kinds of tools we use. One pair of tools that I often confuse is our cheese grater and our foot file. They look very similar, but you shouldn't mix them up. Using the cheese grater on your body is dangerous, and using the foot file on food is deeply unappetizing. I imported a half-dozen packages from Keras and one from NumPy for some matrix manipulation. Then I loaded the parameters, the weights, for VGG16. Note that it was trained to recognize many categories from football helmets to cheeseburgers, but not foot files or cheese graters. I then surgically removed the final two layers that do the classification and left all the previous layers that define the feature set. I took 10 photos each of the foot file and the cheese grater in different orientations, all against a neutral background. We can grab my photos and unzip them. After importing 2 libraries for manipulating images, I constructed a list of the 20 image files. Let's loop through the images and load them in. We'll make them 224 by 224 pixels to match the image sizes that VGG16 expects. We'll squirrel away the image object itself in a list of images called IMGs. To feed it into VGG16, we need to turn the image into an array. But the really slick thing is how we can use VGG16 to turn this image into a feature vector. We feed the image into VGG16 as we would if we were going to predict one of the 1,000 ImageNet classes. Since we had altered VGG16, removing its last layer, what's left is the activation on the final layer of the network before it makes its classification. These vectors capture the deep similarities between images and are fantastic for use in a nearest neighbor classifier. But don't take my word for it. Let's try it out. We'll loop through the images. I1 is the feature vector for the current image. We'll compare I1 to each of the other image feature vectors, I2. We'll use dot product similarity between I1 and I2 using Python's @ operator, and keep track of which image best match has the highest similarity to I1. In each case, the nearest neighbor for the tool is another picture of the same tool, in the same or sometimes reversed orientation. Although VGG16 wasn't trained to recognize foot files or cheese graters, it understands how images work well enough to know which images correspond to the same object. In this example, we used a machine learning classifier trained for one problem, VGG16, recognizing 1,000 different image categories in ImageNet, to solve a related but distinct problem, distinguishing a foot file from a cheese grater. Within the machine learning community, this repurposing idea is known as transfer learning. A big advantage of transfer learning is that a new machine learning problem can be solved with only a small amount of new data and computation. The secret is leveraging previous processing on large amounts of other data. In this case, we created a great household tool recognizer with only 10 training images. It's hard to imagine how to better leverage small amounts of data to such great effect. It's still a bit of an art form to know which previously trained systems to use for transfer. ImageNet includes dozens of categories of household objects: paintbrushes, pencil sharpeners, plungers. It needed to learn visual features for recognizing and characterizing all of these classes. Some of those visual features are probably helpful for characterizing cheese graters and foot files as well. But what if you have a trained network for recognizing different types of trucks? Could transfer learning be used to repurpose this network to distinguish kinds of fish? Maybe not. Now, the point here is not about specific household tools. I wanted to illustrate that the deep learning features that come out of broadly trained networks like VGG16 really do a great job of capturing a notion of visual similarity for objects more broadly. Amazing stuff. So, deep neural networks with many layers arranged to identify and exploit translation invariant features can produce state-of-the-art image classification results. When these results started to appear, it was impossible to ignore deep networks as an essential tool for solving difficult computational problems. After the ImageNet challenge, the overwhelming majority of work in the computer vision field was dominated by convolutional deep networks after 2015. With the phenomenal success of deep networks in computer vision, it was inevitable that other areas of artificial intelligence and computer science would take notice. In upcoming lessons, we'll explore the equally transformative impacts of deep neural networks on text processing and speech processing. But next time, we'll confront a fact that each successful new domain of deep learning has had to confront. Debugging a deep learning program is hard, with elements unlike anything else seen in programming. When you debug a computer program, you're carefully figuring out the right questions to ask. You want to understand why things went wrong and how things can be made right. Since machine learning programs are programs, you can make the same kind of bugs that plague authors of any typical computer program, from syntax errors in the code to logic errors in your own thinking. But in machine learning programs, there's another layer to consider. Even when machine learning programs are broken, they're still trying to do the right thing. And that virtue of machine learning can also interfere with a programmer's ability to see where the error is. The programs don't work as well as they should, but the root cause of the problem can stay hidden, especially in deep learning programs, since they can be so complex. In this lesson, we'll look at some techniques specific to debugging machine learning programs. A machine learning program can go wrong in any of its three main components: the representational space, the loss function, or the optimizer. So debugging a machine learning program requires that we delve into each of them. We need to make sure our instances and labels track each other, and that we haven't corrupted the data along the way. We need to use the right loss function for the job, and we need to figure out how to coax our optimizer into producing useful answers. As you might guess, there's no magic recipe for taming a difficult program. But the strategies in this lesson can help you get things working faster. The best way to show you what to do when things go wrong is to let things go wrong. In most of the examples I prepared for this course, things didn't work on the first try. I had to do debugging, sometimes a lot of debugging, to get the examples to the level where I was comfortable sharing them with you. Not this time. We'll work through an example, and I'll show you my mistakes as I make them. I'll also show you the changes I had to make to get things working. Since we're debugging, I decided we'd create a neural network classifier that can look at images of animals and flag images that have insects or spiders, basically any images of creepy crawly critters. Yes, we're going to find the bugs in a machine learning program that's about finding bugs. That's meta, just like machine learning. Okay, ImageNet is a large collection of labeled images that can be used for classification. It really is large. There are 1 million images. It's too much to use ImageNet as a pedagogical example where we are training and retraining in different ways. Just uploading the images to a Python programming environment, such as Colab, could take an hour before we even start to process them. Fortunately, a machine learning class at Stanford created a smaller version of the dataset where the individual images are scaled down and the number of distinct categories was reduced. Even with this reduced size dataset, a single training run with 1,000 passes through the data could take an hour, and there are about a dozen runs in this lesson. Several times I've mentioned that deep learning leverages graphics processing units, or GPUs, to run quickly. Given the computational costs involved in training models this lesson, I found GPUs essential this time. If you're following along in Colab, I recommend that you do the same. After you load the notebook, but before you run any of the code blocks, select the Runtime menu on the Colab Notebook page. Under that, select Change Runtime. Then select GPU from the menu. Colab will remind you that you should only use GPUs when you really need them. You do. The scaled-down ImageNet collection is called Tiny ImageNet, but it still has 100,000 images, which is kind of a lot for something that's tiny. The dataset consists of 200 categories instead of ImageNet's full 1,000 categories. Each image is a 64 by 64 pixel color image, which is about 1/12 the size of those in ImageNet. There are 500 images in each category instead of ImageNet's roughly 1,000 images per category. We can download and unzip all the image files. We'll import some code for image processing. We'll use Keras for building our neural networks and NumPy for working with vectors. We'll also use a function from sklearn, the scikit-learn library, for splitting up training and testing vectors. From the 200 categories in the set, I picked 36 that correspond to animals. The list includes lions, boa constrictors, and king penguins. We'll combine these individual categories into a new category called animals. I also picked 14 categories from Tiny ImageNet that correspond to bugs. The list includes roaches, grasshoppers, scorpions, tarantulas, and dragonflies. We'll combine these individual categories into a new category called bugs. The readCat subroutine reads the images for the categories cats it is given, and it associates their vectors with the labels in lab. We also pass in the desired training and testing set sizes. Initially, the lists of vectors and labels are empty. We run through all the categories C and images I. For each one, we construct a file name into the tiny dataset. Specifically, the directory that stores the images is called tinyImageNet200/train. Then there's a subdirectory for each of the Tiny ImageNet categories, which contains a subdirectory called images. Within that directory, there's 500 JPEG files, each named with the Tiny ImageNet category and a number. We retrieve the image and store it in IMG. From the image object, we extract an array and flatten it out into a vector. Then we reshape it to 64 by 64 by 3 colors. We string together all the collected images and labels into lists, one list called vex and the other called labs. Once the lists are constructed, we turn the list of vectors into a NumPy array. We split up this array and the labels with the desired train test sizes and return the result. Now we can read the vectors and labels for the animals. That will be our category 0. We'll use 10% of the available data for training and 20% for testing. We'll do the same for the bugs. That will be our category 1. Combining category 0 and category 1 gives us our training and testing sets. Now we have our training and testing data. Next, we need to set up a learner. Since we're recognizing images, it seems like a reasonable place to start is the VGG16 architecture from the vision lesson. It consists of a series of 14 convolutional layers interspersed with max pooling layers. After these layers, it includes 3 fully connected layers, ending with the output layer. In the code to build and return the untrained neural network, the main change is in the very first layer and the very last layer. VGG16 is designed to recognize ImageNet images of size 224 by 224. The tiny images in this set are only 64 by 64, so the input shape is different. The output shape is also different. In the ImageNet challenge, the learners have to pick out an image from 1,000 categories. Here, we only have two, animal and bug. So we'll use a single output unit with sigmoid activation. A sigmoid unit is one that outputs a number near 1 if the input sums to a positive number, and near 0 if the input sums to a negative number, with a smooth transition between them around 0. Thus, the outputs look like probabilities. It is trained to produce a number close to 1 for bugs and close to 0 for animals. Okay, let's try to recognize our bugs. We build the network, attach a loss function and an optimizer to it, and run the training algorithm. It says our accuracy on the testing data at the end was 72%. We'd really like the loss to be a tiny number like 0, but instead we're at 0.28. But maybe that's okay. As debuggers, we need to look a little bit deeper though. Let's try to get a handle on whether that score is good or bad. One important debugging tool is to look at the data. Here's some code for picking a random testing example and showing the associated image. It picks an index at random using the random number generator library's randint command for producing integers in a given range. It prints the associated label yTest for that testing example where 0 means animal and 1 means bug. It pulls out the instance, pre-processes it, and formats the array as an image. I encourage you to run the code and look at some random images from the collection. Can you distinguish the animals from the bugs? I flipped through 10 images and there were 2 or 3 where I wasn't really sure what was going on. So I'd score something like 70 to 80%, which is on par with the algorithm. That suggests that maybe the classifier is pretty good. What does the classifier actually say? It classifies all of the images as animals. Uh-oh. The only reason it gets 72% correct is that the classes are imbalanced. 72% of the images are animals, so always guessing animal seems to do well. No, we want the learner to have to work a bit harder to get a score like 72%. As part of our debugging process, we'll force the two classes to be of equal size. Let's retrain using 500 examples from each class. Then we can rerun and see what happens. 50% correct. Okay, that's good news and bad news. It's good news because we now have an accurate measure that the learner is failing to capture any of the signal in the data. The bad news is that the learner is failing to capture any of the signal in the data. All right. One powerful technique for debugging in general, and debugging learning algorithms in particular, is to give it an input that it has to get correct. What do we expect to happen if we decrease the training size to 10 examples, 5 positive and 5 negative? The neural network model has almost 40 million weights, so with only 10 training examples, we should expect massive overfitting. That is, the learner should easily memorize the training data and obtain 0 loss. But we cannot expect it to generalize usefully to new examples. Is that what happens? At this stage, it's worth checking. Indeed, it gets a measly 50% correct on the testing examples, but it also gets the same poor 50% correct on the training examples. Something is definitely not right. Our learner is not responding in a meaningful way to the training data. We will focus on that issue first and then worry about generalization to the testing data. Let's take a look at the optimizer. Well, one issue is that the optimizer is only running for one epoch, one pass through the data. That might be enough if we have millions of examples, but with only 10 examples, we're going to need to update the weights many times per training example to see meaningful learning. Let's rerun for 1,000 epochs. I turned off verbose mode because otherwise the screen would be flooded with 1,000 status updates. Instead, I'll just print the loss and accuracy at the end. Nope, still getting 50% in training and testing. Neural networks were extremely popular in the late 80s and early 90s. A major cause for their falling out of favor was that it was difficult to train networks with more than 2 layers of weights. One of the reasons for this problem is that gradient computations are multiplicative. That is, the gradient at one layer is computed by multiplying weights times the gradient of the previous layer. Think of what that means when there are a dozen or more layers. If weights are typically less than 1, the product will dive to 0. If the weights are typically more than 1, the product will rocket towards infinity. The range of weights for which the gradient values are likely to remain in a meaningful range is pretty narrow. This problem is often referred to as one of vanishing or exploding gradients. To get a deeper appreciation for the problem, let's look at a concrete but very simple example. Consider a neural network that maps a single input to a single output. It has 9 layers of weights, and each neuron has a linear activation function. That means that when we present an input X to the network, it gets multiplied by the first weight W1 to produce the activation in the first hidden unit. With a linear activation function, this value remains unchanged, and then is multiplied by the next weight W2 to produce the activation in the second hidden unit. This process continues until we get the output, Y, which will be the input multiplied by all of the weights in the chain from input to output. In a more complex network with multiple hidden units in each layer, the output is the sum of chains like this over all possible paths from input to output. If the input were 1 and the weights had values around 5, then the output would be around 2 million. On the other hand, if the weights had values like 0.1, the output would be around a billionth. Initializing weights to be around 1 keeps the activations from blowing up or collapsing. The same holds true for the gradients, even more so. In this simple network, the magnitude of the gradient is roughly the square of the output. Giant values get even bigger, tiny values get even smaller. One way to keep activations from exploding is to use an activation that squashes big inputs. Activation functions like sigmoid and hyperbolic tangent, tanh, were very popular in the 80s and 90s, and they served this purpose. They are effective at preventing explosions in activations, but they do so by flattening out the gradient at high and low activation levels. The gradient of tanh at 5 or -5 is about 200 thousandths. Since weight updates are proportional to the gradient, that means many updates are needed to move the weights when the gradient gets tiny. Several techniques help tame these vanishing or exploding gradients in neural networks. Switching from sigmoid or tanh activations to ReLU helps eliminate the vanishing gradient problem. The gradient of ReLU is one that's either 0 or 1, no matter what the input is. As a result, the gradient is likely to move the weights quickly, if it moves them at all. But ReLU activation still suffers from the exploding gradient problem if activations get big. This problem is mitigated by initializing all weights to values in the vicinity of 1. That way, activations never get significantly magnified or reduced as they propagate through the network. These algorithmic ideas played an important role in enabling the deep learning revolution, along with the availability of data and increases in computer power. We've already been using Keris's default weight initialization and ReLU activation functions, so we're probably okay, but let's take a look just to make sure. Since weight updates are proportional to the size of the gradient, an exploding gradient will manifest as extremely large weights in the network. Let's take a look to make sure the weights haven't gotten too big. Running getWeights on the learned model will dump all the values for us to see. There are a lot of them, but flipping through, the weights seem to be in a reasonable range. I don't see anything bigger than 1, for example. So exploding gradients is probably not our problem. Vanishing gradients are a lot harder to spot. They manifest as no weight changes at all, especially in the layers closest to the input. An important technique is normalizing or pre-processing our instances so they're in a range of values likely to pass through the network well. Keris includes a library with some image processing useful to VGG. We'll use the preprocessor to prepare the data for learning. After translating the image into an array, we apply the preprocessing routine to it. The resulting image array is then flattened and then reshaped into a 64 by 64 pixel array with 3 color channels representing red, blue, and green. As we saw, activation functions are most reactive to their inputs when those inputs are in the -1 to +1 range. So since pixel values are 0 to 255, we'll rescale by dividing by 128 and subtracting 1. That makes the smallest value 0 divided by 128 minus 1, or negative 1. The largest value becomes 255 divided by 128 minus 1, or roughly positive 1. This modification did not improve matters. We're still getting 50% error on both training and testing. The preprocessing is likely useful for learning, but it didn't help here. It's a trick that's more useful for taming exploding gradients than vanishing ones. Our program is getting better, but it's still plagued by some problem we haven't identified yet. Perhaps what's going on is that we have a very tiny training set and we're only running through it 1,000 times. Maybe that's just not enough to move the weights to where they need to be. We don't want to increase the training set right now. That's because we're trying to debug why we're not seeing learning happening even on a small example. This is where the network ought to be able to simply memorize the inputs. We could increase the number of epochs used in training. That could slow things down a bit, while the weights will have a chance to move in the right direction. Or we could also just take bigger steps by increasing the learning rate. Increasing the learning rate should let us see a change quickly, but it's a bit risky because big updates can cause the learner to overshoot, missing out on what could be more appropriate weights for the problem. Still, it's worth a shot. Ha! Hallelujah! We're getting 60% accuracy on the training data now. It's finally listening to us. Performance on the testing data is poor, just 49%, but that's okay. We are not yet training the classifier to be good. We were just trying to get it to react. Let's increase the size of the data in the training set from 10 to 100, 50 animals and 50 bugs. We'll retrain for 1,000 epochs. That's how many times the algorithm will run through the training data. Accuracy on the testing data is up to 55.8% now, and that's encouraging. Let's increase the size of the training data from 100 to 10,000 by increasing the number of training examples in each of the two categories to 5,000. Since there are more training examples to move around and move the weights around, we can cut back on the epochs a bit so training time doesn't increase too much. Let's change the epochs from 1,000 to 100 epochs. Takes a few minutes to train, even on the GPUs. Without GPUs, I could not get it to run even 50 iterations in under 13 hours. Using the GPUs, running 100 iterations took about 15 minutes. And the results are pretty solid. We're getting 80% accuracy now on the testing data. It's about how well I did when I tried to recognize the images myself. If we could increase the size of our data by another 3 or 4 factors of 10, up to 10 million or 100 million, we might be seeing astonishingly good performance. Deep learning is a data-hungry beast, but it repays such contributions with improved accuracy. Since we're not going to go out and collect our own additional data, we're pretty much maxed out now. If we want to improve performance further, we'll need another approach. One thing to notice is that we're strongly overfitting, with 99.7% accuracy on the training versus 80% accuracy on the testing set. In principle, when we have a classifier that is generalizing properly, these numbers would be the same. So that suggests we need some regularization and maybe we should use a smaller representational space. Given that our VGG16 network has about 40 million trainable parameters, thinning out the representational space to have fewer parameters seems like a sensible idea. At this point, we could do various architectural tweaks. Try another convolutional layer, change their kernel sizes. We could increase or decrease the number of convolutional features. Maybe you can see why it's so common to just reuse something that other researchers have found that works. The space of possible tweaks can be overwhelming. We could also move the learning rate up or down, or maybe change the optimizer or number of training iterations. All these different kinds of modifications are collectively called hyperparameter search. If the parameters of the network are the weights, the hyperparameters are the parameters like the learning rate that influence how the weights are found. We've not been very systematic about setting the hyperparameters, but if we had a lot more computer power at our disposal, we could run hundreds or even thousands of different combinations of settings all at once to find what works best. And that's something that machine learning people often do. It's referred to as grid search because you can think of combinations of hyperparameter values as points on a grid. Also, the computer clusters where these searches take place also happen to be called grids. A grid search really just amounts to a loop over parameter values. We might want to try 20 different learning rates, 2 different optimizers, 5 different initial random weights, and 10 different network architectures. That's 2,000 repetitions, so that's 2,000 times longer to run. If learning takes 10 minutes, then this grid search would take 5.5 days. If learning takes 5 hours, the grid search would take 13 months. Of course, people doing grid search don't wait 13 months. They use 2,000 computers and get the results in the same time that they would spend on just one run. Of course, the people that can do that are the people who have 2,000 computers at their disposal. Generally speaking, those are big computing-centric companies, not your average Joes. One final technique to mention, whose apparent efficacy outstripped the ability of researchers to explain why it works, is batch normalization. Introduced in 2015, batch norm, as it's known for short, can dramatically reduce the number of epochs needed to train a deep network. Batch norm changes the behavior of layers inside the neural network. Specifically, it shifts and scales a unit's output value so that it is mean 0 and variance 1 with respect to the batch of data the network is processing. You can tell Keras to use batch normalization by running keras.layers.batchNormalization on a layer of the network you are constructing. Batch norm is not a debugging technique per se, but it is an important technique for making deep networks train more consistently. It keeps the activation on units in the -1 to +1 range where, as we've seen, gradients are best behaved. Let's pull together what we've learned about debugging a deep learning system. I think a helpful way of organizing our knowledge is in terms of debugging along 3 dimensions that define a machine learning program. There's debugging we do on the loss function, and debugging we do on the optimizer, and debugging we do on the representational space. Let's start with how loss is being computed. It's a good idea to watch out for class imbalance. If there's way more of one class than the others, typical loss functions will skew the results toward only caring about the majority class. Using similar amounts of data across the classes can help. Or if the classes do not have similar amounts of data, there are loss functions that weigh the different training instances differently to shift things around to compensate. It's important to look at your data as a sanity check before and after it's input into the network. Is it corrupted? Is the important signal being overwhelmed by noise or errors? Did the labels get assigned correctly? Make sure your data is clean. The loss of your network is measured with respect to the data, so messed up data will mislead the training process. An easy error to make is applying some kind of transformation on the training data, but then forgetting to do the same transformation on the testing data. The loss surface is also significantly affected by the amount of training data. Get enough training data. Overfitting, significantly better training performance than testing performance, is a sign that more data is needed. In machine learning of all kinds, optimization is the main service the computer does for you, but it can also be the most frustrating piece to debug because it's very much out of your control. In my opinion, one of the big contributions of the deep learning revolution has been the idea that we can just wait longer. In the 1990s, if we weren't getting good results after an hour or so of training, we'd give up. In the 20-teens, deep learning runs took days or weeks despite using computers that had become a lot faster. It's a good things come to those who wait approach. If you don't want to wait longer, you can also get more processors or faster processors. GPUs and TPUs can do the same amount of work in a fraction of the time because they're so well optimized for the operations that deep learning systems need. They can be expensive and they can use a lot of energy, but they are fast. The learning rate parameter has a big impact on optimization results. Low learning rates can do a better job of tuning the weights accurately, but high learning rates can cover more ground in the search more quickly. If you conclude that weight updates are too slow, increase your learning rate. If you conclude weight updates are too erratic, decrease the learning rate. Packages like Keras can do some automatic tuning of the learning rate, but with enough experience, a person can often do much better and much faster. If you need the best performance money can buy, do a grid search on any hyperparameters that you aren't already confident in. That's how the big players squeeze the best performance out of their networks. Include the optimizer itself in the search. We use the Atom optimizer in this lecture, but others include SDG and RMS prop. Switch it up a bit. But even small players have control over the representational space for the learner. If you were underfitting, getting low performance even on small amounts of training data, you might need a bigger network. More parameters provide more power for expressing more specific patterns in the data, and they can make the optimization problem easier as well. I've found it useful to train on simplified artificial data or small amounts of data to make sure the network can carry out the necessary computations. Or you might train on a real-world data set that's known to be easy. MNIST is a good example in the visual domain. An annoying error is to freeze or unfreeze the wrong weights. If we're using a pre-trained encoder, like we did in the vision lesson to recognize household tools, we don't want the weights in part of the network to change. We can tell the machine learning library to lock them in place. Other weights should be allowed to change to fit the data. If we get these things backwards, it can help to standardize the features entirely, changing the scale and shifting so they have 0 mean and a variance of 1. Batch normalization standardizes for you. Normalizing can make it easier for the optimizer to find weight settings that transform the inputs into a form that's easier to manipulate. Even if we get all of these many things right, we can still run into trouble. In my experience, things going wrong is not a rare occurrence. Optimization is hard. Sometimes there's just not enough signal in the data to learn a good rule. But keeping in mind these vulnerabilities in the loss, the optimizer, and the representational space can help get you back on track when things do go wrong. One last word of advice. Question your assumptions. Ask yourself, why do I believe this should work? You might feel really sure that what you're doing ought to work, but maybe it just shouldn't. Ask yourself for evidence, and gather the evidence if you don't have it. Checking what you believe should work and the evidence for that belief, you're likely to discover that the bug wasn't in the program, it was in your thinking all along. It's kind of magical to watch a computer learning to see. Not bug, bug, not bug, 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 not bug. Bugs be gone! Good job, network. Debugging a machine learning program can be time-consuming and frustrating, but when you finally get it working well, it's an amazing feeling. Machine learning gives us a whole new toolkit for representing and acting on the meaning of words that goes far beyond what was achieved in earlier systems that used handwritten rules to process language. The starting point for the machine learning approach to understanding natural language is language embedding. The idea is to use machine learning to capture statistical relationships between words by associating each word with a high-dimensional vector. Language embedding is used whenever we need to capture the meaning of words, which is an important component of processing language. Because language embedding maps words to vectors, it's also known as word-to-vec. There are many natural language tasks a computer might be able to help you with. In the Bayesian lesson early on, we talked about spam filtering. That's like asking the computer to look over your email and take out the junk messages before you look at them. You might want your computer to help catch typos. That's the problem of spelling correction, or the interactive version known as autocomplete. Extracting text from images or audio can also be very useful. These problems go by the names optical character recognition and automatic speech recognition. In all of these applications, the computer needs to be able to evaluate text and differentiate between likely and unlikely sequences of words. We call a system for assigning probabilities to sequences of words a language model. In this lecture, we'll see how we can use machine learning to help construct accurate language models from data. We know that neural nets are great with low-level perceptual data, but what we'll see this time is how neural nets also came to be used for keeping track of what words mean and classifying text based on leveraging these language models. In Lesson 14, we saw that two sorts of breakthroughs were made possible in vision by convolutional networks. First, convolutional networks were essential to greatly improving performance on a particular task, recognizing objects and images. But they also turned out to provide a fantastic representation for many other problems in image analysis. That is, we saw that we can train up a deep convolutional network for one problem and then transfer the internal representation it learns as input features for related problems. A similar reusability breakthrough happened in language modeling too. It turned out that the internal representations used to capture relationships between words could also be reused when solving a variety of other natural language processing problems. For reusing representations in language models, the crux of the idea is words can be represented as vectors of numbers. And that's helpful because neural networks are programs that map vectors of numbers to other vectors of numbers. So if we can represent words as numeric vectors, that might provide a foundation for using numbers to do various kinds of language processing tasks. More specifically, we'll want vectors to be similar to the same degree that the words being represented have similar usages. The most basic form of this idea is to make a kind of numerical dictionary. Each word in English is assigned a numeric vector definition. A former supervisor of mine, Tom Landauer, pioneered creating numeric vector definitions for words back in the 1980s. Using this idea of defining words with vectors, he started a company to automatically grade essays for standardized tests. Whether an essay was on topic was assessed based on how close its vector representation was to examples of ideal essays. His system did a great job of characterizing meaning, and the work suggested that even more useful systems could be created if they could be built from bigger data sets. He also made a joke when he talked about the idea. He'd say that after much thought and much computation, he can now reveal the meaning of life. And then he'd show a high-dimensional vector. It's the numeric definition that his unsupervised learning algorithm found for the word life. Maybe it's not quite the philosophical breakthrough he was teasing, but it does raise some interesting philosophical issues. Can meaning be captured through the manipulation of numeric vectors? You might be surprised to see how much about meaning can be captured this way. Let's start by looking at Landauer's language embedding method, latent semantic analysis. It is called latent because it is finding hidden dimensions that characterize the data. Our starting point is a collection of texts. It could be a bunch of newspaper articles or maybe encyclopedia entries. The set of distinct words in this collection become the rows of a matrix. Maybe there are 10,000 such words. Each text of the collection becomes a column. A typical collection might be 3,000 documents. Then a cell in the matrix is filled in with the number of times the word for that row appears in the document for that column. So we want to create a vector definition for each word, such that two words that have similar meanings will have similar vectors. The assignment of words to position in space is called an embedding. I could make a three-dimensional embedding by placing words like cat and dog in physical space. Typical word embeddings use hundreds of dimensions, but the idea is the same. One way to measure how similar two vectors are is using vector cosine. That's the normalized dot product. It measures the angle between the embeddings of the words, where the cosine similarity of a vector with itself is 1. Cat and dog have a small angle, which corresponds to a large cosine, close to 1. The cosine similarity of two vectors that point in completely unrelated directions is 0, and the cosine similarity of two vectors pointing in completely opposite directions is -1. Anyway, related words like cat and dog will appear in a similar pattern of texts, so their rows of the word text matrix are likely to be vectors with high cosine similarity to each other. Now, whatever we do, let's make sure to avoid the biggest pitfall in machine learning: overfitting. Remember, we started with 3,000 texts, so a row of the matrix for any word is a vector with 3,000 dimensions. We might do better if we approximate the information in the matrix using fewer parameters. If we limit the size of our representational space, we can combat overfitting. The fundamental trade-off is that too few parameters is bad because that will tend to wash out important distinctions between words. Too many parameters is bad because that would retain noisy distinctions that aren't broadly meaningful. That's the essence of overfitting. In practice, approximating our matrix of 3,000 dimensions with just 100 to 300 dimensions does a really nice job across a range of methods, data, and applications. But how do we decrease the dimensionality of a matrix? To solve that problem, we can use a result that dates back to 1907. We can optimally approximate the dot products of vectors in high dimensions using vectors in lower dimensions. Linear algebra tells us that any matrix can be rewritten as the product of three special matrices. The first gives a re-representation of the rows so that each row is independent of the others in terms of a set of internal factors. The second is a diagonal matrix giving the importance of each internal factor. And the third gives a re-representation of the columns, so each column is independent of the others in terms of those same factors. The rows of the first of the three new matrices can be used as the vector definitions of the words. And now we're in a position to reduce the dimensionality of these vectors. The great trick comes from the fact that the second matrix tells us which factors are most important for capturing the original matrix. To get a lower dimensionality, we'll just drop all but the 300 most important factors. The solutions to all the approximation problems nest inside each other, so taking the best 300 dimensions is automatically the best you can do with 300 dimensions. Taking the best 100 dimensions is the best you can do with 100 dimensions, and so on. We don't perfectly match the original word by text matrix, but we end up with the best 300-dimensional reconstruction of it. Latent semantic analysis then takes the rows of the word by 300 factor matrix as the embedding. The mathematical operation we performed here is known as a matrix factorization, or singular value decomposition. The name refers to the fact that the decomposition can be used to determine how close a matrix is to being singular, or numerically unstable. This decomposition can be carried out pretty efficiently, even on pretty large matrices, up to, say, tens of thousands of rows or columns. You can think of it as a kind of machine learning optimization, where it's trying to find the best low-dimensional reconstruction of a bigger matrix. It's an unsupervised method because it is learning a representation using only unlabeled data. Here, best is defined by our loss function, which is the total squared difference, or squared error, between our original matrix and our reconstruction. Landauer and his colleagues showed that the resulting embedding captured a lot of interesting knowledge about words and their relationships. It discovers general trends about word usages that can be exploited to solve other problems. For example, vectors can be used to answer synonym questions from the Test of English as a Foreign Language exam at a level close to that of the average of the applicants taking the test. Even the mistakes it made correlated with those of the test takers. These multiple choice questions consist of a question word, like credible, followed by 4 possible synonyms. The correct answer is the word that most closely matches the meaning of the question word. In this case, the answer is trustworthy. To ask the language model its opinion, we have it look up the vectors for each of the words. Then we have it select the word whose vector has the highest cosine with the vector for credible. Now let's transition to modern neural network approaches to the problem of language embedding. The singular value decomposition used in latent semantic analysis is closely related to an unsupervised neural network learning approach called autoencoding. An autoencoder is trained on a set of vectors, like the rows of the word text matrix we've been discussing. It's trained to map a vector from its training set as an input to precisely the same vector as an output as accurately as possible. Along the way, the vector is compressed such that a smaller number of units is used to represent the original. The activation on the hidden units is an embedding of the input vector. If the network has a hidden layer and only linear activation functions, the set of learned weights can be directly related to the singular value decomposition matrix approach. But formulating the problem as a neural network opens the door to more powerful approaches. In 2014, word embeddings were taken to the next level. Researchers at Google figured out a way to train embeddings based on massive amounts of text, billions of words instead of tens of thousands. They used neural networks and created the embedding as the solution to an unsupervised learning problem. Using neural networks allowed them to use nonlinear transformations instead of the purely linear decomposition used in latent semantic analysis. They defined a good embedding to be one where the embedding for each word is useful in predicting the embedding of other words that appear near it in a large corpus of text. The representational space was again one vector per word. The loss function can be decomposed into pieces as follows. At each position in the training corpus, we have a word and its neighbors. Here's the word word and 5 neighbors on either side of it from the corpus. For this example, the corpus is the transcript of this lecture. We want to model the probability that a word near will appear in the neighborhood of word word, probability of near given word. We estimate this quantity by computing the dot products of the word's vector with the vector of every other word in the vocabulary. We exponentiate the values so they're positive. Then we normalize by the sum so they add up to 1, summed over the entire vocabulary. We can interpret these numbers as predictions, from the word's perspective, of what neighbors the word expects to have. This approach is called GLOVE. The name comes from global vectors. The loss used in GLOVE is a function of the probability the learned model assigns to the training data, which words appear near each other. To keep the numbers from getting too tiny, the method maximizes the log probability. Using logs converts a giant product of probabilities into a much more tractable sum of log probabilities over all of the word positions. We negate the quantity to make it into a loss. The higher the probability the vectors assign to the words that appear actually in the neighborhood, the lower the loss. A gradient descent-based optimizer can figure out how to assign values to the vectors to minimize this loss. And the results are pretty impressive. We can ask it to arrange the words in 100-dimensional space based on 1 billion words of text. The resulting arrangement has some amazing properties. One of its striking features is its ability to solve analogy problems, which we talked about in Lesson 10 on machine learning pitfalls. The goal of a pre-trained word embedding, like latent semantic analysis or GLOVE, is to capture some of the patterns in a word's usage. But instead of sequences of words, what's captured is a vector, which neural networks can process more easily. Let's take a look at one of the many possible uses of a pre-trained word embedding. The problem of text categorization is to take a document and to figure out which of a set of predefined categories the text belongs to. A lot of problems involve putting text into categories. A company wants to organize its large collection of internal documents so that all documents pertaining to a specific project get filed together. The projects are the categories. Companies like Pinterest want to keep the content on their site upbeat and positive. To do so, they categorize the text that users enter into their site as being either safe or suspicious. Suspicious postings might get flagged to be hidden or removed. Text categorization also helps voice interfaces do the right thing. Amazon's Alexa voice assistant classifies what it hears into categories that correspond to different kinds of actions it can do and information it can provide. Was that a question about a celebrity, the weather, or a request to turn on the lights? Users can create their own apps for Alexa using the Alexa Skills Kit, also known as Ask. In the programming interface, you include lists of example sentences so Alexa can classify what it hears into the categories you define. As a concrete example of text categorization, we're going to work with a well-known dataset from the early days of the internet. The dataset is called the 20 Newsgroups Collection. It was gathered from a kind of discussion board that was popular back in the 90s. Each time a person would post, they would do so in a particular newsgroup category. The 20 Newsgroup Collection includes postings from 20 different newsgroups. The full collection is available through the scikit-learn library in Python, which is very cool. We just need to import the command fetch 20 newsgroups, and we can start using the dataset in experiments. To keep things simple, we'll just focus our experiment on 2 of the 20 newsgroups, corresponding to posts about baseball and about hockey. We load all the relevant data from the posts into a variable named newsgroups. When I looked through the data, I thought the heads and quoted text and footers really cluttered things up, so I removed them. Now, I'm going to be talking a lot about words, and I'll be talking about them in 2 distinct senses. In this brief passage from a writer by the name of Steve Martin, how many words does it have? Well, it's 13 words long, so 13, but there are only 10 different words, so 10? In the field of statistical natural language processing, researchers have different words for these 2 word concepts. We say that the passage consists of 13 tokens, but only 10 types. For example, have, people, and way are types, and each of those types happen to have 2 tokens. The 7 other types have 1 token each. So a type is a word name, while a token is an appearance of the word. It's kind of like Dalmatian is a type of dog, but the famous story has 101 tokens of this type. Let's download a copy of the pre-trained embeddings produced by the GloVe embedding system. It was trained on 6 billion words of text, 6 billion tokens. It includes embeddings with 50, 100, 200, and 300 dimensions. It's a big file and can take about 5 to 10 minutes to load. I'm putting the vectors in a dictionary called embeddings index. Some Python code can read in the file f and store each word vector in it. We'll work with the 100-dimensional embedding stored in glove.6b.100d.txt. Give the index a word, and the index will come back with the vector assigned for that word. Each word name, each word type, has a vector. There are 400,000 types in this collection. Since it had 6 billion tokens, that's an average of 15 tokens per type. We're going to need to process the newsgroup documents into vectors. The deep learning library Keras gives us some tools for converting words into numbers. We set a maximum number of distinct words to 20,000 types and the maximum length of a sequence or document to 1,000 tokens. We use a tokenizer to process the strings of letters corresponding to the newsgroup posts into sequences of numbers, 1 sequence for each word. For example, the word goal corresponds to a vector with 100 dimensions. The mapping from words to their associated numbers is stored in word index. We'll need that in a moment. We now have 2 different dictionaries, or indices. Word index holds the mapping from words in the newsgroup postings to word IDs. Embeddings index holds the mapping from words to vectors. Note that they aren't exactly the same set of types. There could be words that appeared in the embedding training set that are not in the newsgroup postings, or vice versa. We're now going to fill in the embedding vectors for the types in the newsgroup postings. We start with a matrix of zeros. The dimensions of this matrix are the number of types found in the newsgroup postings by the vector size in the pre-trained embedding. We have a for loop to go through the types appearing in the newsgroups. We use the continue statement to skip anything that appears less often than max num words highest frequency types. Otherwise, we look up the embedding vector for the newsgroup word type and store the embedding vector in an embedding matrix. If the newsgroup collection has a type that was not given a pre-trained embedding, its embedding vector will be none. No vector will be filled in for that type, it will just remain a vector of all zeros. Okay, time to prepare the data for the neural network we'll construct to process it. A lot of the cutting-edge art of using neural networks for solving machine learning problems is constructing an architecture well suited to the problem at hand. What we're trying to do here is map documents consisting of a sequence of words into one of 2 categories. The fact that our 2 categories happen to be baseball and hockey is probably not important to our choice of architecture. What is important is extracting as much higher order meaning as possible from the documents. In Lesson 6 on naive Bayes, we focused on bag of words representations that ignore word order. It's not a bad approach, especially when data is in short supply. But this time, we'd like to take advantage of word order. That is, if words appear next to each other, that's something that might be relevant to deciding whether a document is about hockey or baseball. And if we want to detect short phrases, then we've already talked about a tool that's really good at picking up on this kind of local structure. In Lesson 14 on image recognition, we saw the idea of convolution, the technique that scans a window over an image to find informative features from the patches in the image. Those were 2D convolutions, but here all we need is a 1D convolution. A one-dimensional convolution extracts information from contiguous patches of words. How many convolutional layers do we need? Well, for this simple example, we'll use a sequence of 3 convolutional layers, which are marked with green, orange, and blue trapezoids. Each convolutional layer will have a kernel size of 5, which is just another way of saying units will look at groups of 5 consecutive words, specifically 5 consecutive tokens. Each of the empty rectangles in the diagram contains a vector. The top row of vectors comes directly from the vector embedding by GloVe. The first convolutional layer, in green, looks at windows of 5 input tokens. The second and third convolutional layers, orange and blue, each include the output of the 5 convolutional filters applied to the previous layer. After 3 rounds of convolutions, we'll predict the category using a fully connected layer. It's really a lot like what we saw in the vision lesson, except applied to sequences of words. For this example, we'll make all of the documents exactly 1,000 tokens long using a predefined auxiliary function called pad sequences. It extends sequences with zeros, so the sequence will be the determined size. Pad sequences chops off the end of a sequence if it is too long. We'll also convert the 2 output categories into a pair of values. We'll let baseball be 1, 0, and hockey be 0, 1. This representation is sometimes called one-hot because each category is represented by a vector with a single 1 in it. With the document instances and category labels ready to go, we can do a train test split to divide them into a training set of size 200 instances and leave the rest of the instances for evaluation. From the Keras library, we'll bring in subroutines to build our chosen network architecture. Since we want to train our network in 2 ways, we'll make a function called train with a parameter pre-train that we can set to true if we want to use a pre-trained embedding and false otherwise. The only place the network depends on the pre-trained parameter is in the embedding layer. In the network with no pre-training, we set these weights to be trainable. In the network with pre-training, we initialize these weights from the pre-trained embedding and set them to be not trainable. We create the input layer from word sequences. The embedding layer takes the sequence input and creates embedding sequences. It maps the token identifiers into vectors. The idea is that each token is replaced by a corresponding vector. Now the layers that turn the words into vectors are in place. We'll make a sequence of 3 convolutional layers to process these vector sequences. Each convolutional layer creates 128 features at each position in the sequence. They have a kernel size of 5. Each layer ends with max pooling. That means that if a feature is present in any position within a neighborhood of 5 around a given location, then is considered present at that location. We have the global max pooling layer pool information across all of the windows. The 128 features that were constructed are finally collapsed to the output using a complete set of weights, or a dense layer. We're using a softmax activation function here. Softmax automatically normalizes the activations across multiple units so they sum up to 1. It's a way to convert arbitrary activations into a discrete probability distribution. That's a good match for the one-hot outputs we're training the network to learn. Now the structure of our network is in place. In standard machine learning terms, it is the representational space for the classifier we want to learn. We can set up a solver for Keras to use. I used the optimizer Atom and set a few of its parameters. As it turns out, I had to work hard to find good parameters for the Atom optimizer. In particular, when I set the learning rate parameter too small, learning was slow. When I set it too big, there was no learning at all. The accuracy rate was only 50%. Because there are only 2 classes, 50% is no better than random guessing. When we hear about a successfully trained neural network, we should wonder how many unsuccessful attempts were made along the way. But think of it like this. I can do a trick, and it looks like it worked on the first try. It's a bit less impressive when I show you some of the failures I made along the way. The people who have mastered deep learning methods will often first go through a bunch of failures by running hyperparameter search, like we talked about in the previous lesson. Now that we've specified our network and solver parameters, we can specify the model's input units as sequence input and prediction output units of the network as preds. We want a loss function that encourages the network to make the outputs look like accurate probabilities. The cross-entropy family of loss functions set the loss for our model to be categorical cross-entropy, which is a standard way to make output sum to 1. Then, we run our machine learning algorithm for 100 iterations on the data, measuring accuracy using the validation data. Running the deep learner we've just constructed gets us a classifier that is accurate 83% of the time. Is that good? Well, it's better than I was able to get with a few other classifiers we've talked about, naive Bayes, decision trees, or nearest neighbors. I also tried one other algorithm to really focus attention on the pre-trained word embeddings. I ran the same text categorization experiment with the same network, but with one tiny change: no pre-trained embedding. The not pre-trained version that had to learn its own embedding from the newsgroup data was equally accurate on the training set. Both got 98.5% correct. But not pre-trained generalized less well to new postings. It got 76% correct compared to the 83% with the pre-trained version. In a sense, the pre-training lets the system do well with fewer tunable parameters. It's kind of a very well-informed regularization. And that's the main lesson of pre-trained embeddings. We can use generic text data to learn about the relationships between words. Then we can use task-specific data to solve the problem at hand. The key idea of word embeddings is to define the meanings of words using vectors in high-dimensional space. These embeddings are learned in an unsupervised fashion thanks to techniques from linear algebra like singular value decomposition. Word embeddings can also be generated using deep learning by using nonlinear functions to generate representations that can predict nearby words. Either way, words that appear in similar contexts get assigned similar vectors. Of course, one shortcoming of word embeddings is that they have to grapple with words like duck. Should we embed the word duck near dodge? Or should we embed duck near chicken? Duck is a funny word in more ways than one. This polysemy problem is one of the things that makes language processing a continuing challenge for machine learning. Still, embeddings can pick up on subtle patterns of word usage, detecting synonyms and even solving analogy problems. Finally, word embeddings trained on billions of words of English can help improve core natural language processing tasks like text categorization. Unsupervised learning and word embeddings are a key technology for creating automated tools for understanding natural language. But by themselves, they're not great at producing language. So in the next lesson, we will expand our toolbox of machine learning approaches to encompass language production. We'll see how to process vectors more flexibly and allow machines to compose text. On long family car trips, we used to make up stories together. Everyone in the car would take a turn adding a word to the end of the story so far. Machine learning systems can output sequences through a similar process. Words are added one at a time, with the computer trying to find a sensible extension to what it already produced. In this lesson, we'll talk about how neural networks can be trained to take their own text outputs as inputs so they can process and produce longer and longer sequences of text. Since what is needed is a mapping from sequences to sequences, such problems are referred to as seek-to-seek. Seek-to-seek problems come in many forms. Continuation is like repeated autocompletion. The input is a sequence of words, and the output is an extended sequence of words that reasonably continue what has been expressed so far. If the input is, "I'm sorry, but you are going to have to," a continuation could be, "Come back and talk to me later," or a zillion other possibilities. The more natural the continuation, the better. Text summarization is the problem of taking in a long sequence of words and producing a shorter sequence of words that conveys the same meaning. Using the sentence I just said as input, a reasonable output might be, "Text summarization makes sequences shorter." In image captioning, the input is a picture, while the output is a verbal sequence describing the image. If the image is a picture like this one, the output should be something like, "A dog is wearing a Santa hat." Language translation takes in a sequence of words in one language, called the source language, and then re-expresses it in another language, called the target language. All of these examples are problems that might train on millions of instances to produce an appropriate sequence of words as output. Let's dive into a neural network approach to translation, which has been called neural machine translation, it's an important problem whose output is a sequence. Because people have already translated material into different languages to share business documents or movies or books, there is a reasonable amount of training data out there, at least for some pairs of languages. The European Union mandates that all official documents be translated into all 24 of the languages of the member countries. For instance, if we want to train a system to translate Danish to Dutch, or any of the other 155 pairs, we'll find the data to do it. It can be tricky to get large amounts of parallel text for less common language pairs, like if we want to translate Yiddish into Navajo. We could do what people have always done when they can't find translators who know both the source and the target languages, translate through some more widespread language, like English. It's not ideal, but that was how many early machine translation systems worked, including at Google. Google started offering their first online translation service, Google Translate, in 2006. It used a phrase-based translation model. It was pretty useful. It served as a kind of online translation dictionary. But the fluency of the translations it produced wasn't good enough to result in readable text. By 2016, the deep learning revolution was in full swing, and Google was using machine learning methods to try to catch and pass their earlier effort. One of their first attempts to apply deep learning to translation matched the performance of their existing phrase-based translation. That's impressive, but probably not worth tossing the old system in favor of the new. The first deep learning attempt at translation was also too slow to deploy at a large scale. There were several rounds of architectural improvements that increased accuracy and clever engineering ideas that increased speed. In September 2016, Google announced that they had a neural machine translation system that could replace the original Google Translate. The differences were indeed impressive. For some pairs of languages, like English to Spanish and French to English, overall performance was on par with that of human translators. But the first language pair Google rolled out using the neural machine translation approach was Chinese to English. Here's an example from their announcement post to give you a sense of the improvement in quality. In the first column, I put a human translation of a Chinese sentence. It reads, Li Keqiang will initiate the annual dialogue mechanism between premiers of China and Canada during this visit and hold the first annual dialogue with Premier Trudeau of Canada. The phrase translation says, Li Keqiang, Premier, added this line to start the annual dialogue mechanism with the Canadian Prime Minister Trudeau. Two prime ministers held its first annual session. The sentence is pretty typical for state-of-the-art translators before deep learning. The word premier doesn't quite fit, and the transition between Trudeau and two prime ministers doesn't work at all. You can tell that the original sentence must have been about starting a dialogue between Canada and China that takes place every year, but it's tough to tell much more than that. The phrase translation stayed pretty close to the ordering of the ideas in the original. I colored different chunks in the sequence: red, blue, orange, black, green, magenta. You can see that the human translation deviated in two significant ways from this ordering. The black chunk from the middle got moved to the end. A new yellow chunk was also added. The human translator stays close to the original, but is open to moving things around to make the meaning clearer. Now let's look at the neural machine translation. Li Keqiang will start the annual dialogue mechanism with Prime Minister Trudeau of Canada and hold the first annual dialogue between the two premiers. It's much more fluent. The details seem clear. Everything fits. The translation moves the green chunk to the end where it flows a lot better. And that's similar to what the human translator did, separating the black and green chunks because they're awkward right next to each other. That was the state of neural machine translation when it started to reach the public circa 2016. Accuracy and speed continued to progress after that point. So how do we formulate the problem of mapping between languages as a machine learning problem? And how do we go about training a neural machine translation system in particular? The neural networks we've talked about in previous lessons have had a fixed set of inputs and a fixed set of outputs. So if we're translating English to Spanish, we'd pick a maximum sentence length. For this example, let's start small and say our maximum sentence length is 8 words. Our basic network might look something like this. The white rectangles represent words, so they'd be groups of input and output units with 1 unit per word in the vocabulary. To represent the word dog, it would have a 0 in every position except a single unit corresponding to the word dog would be turned on. The blue rectangle represents all the processing layers of the network, whatever the number and structure of those layers might be. At this point, we're not going to worry about the details, just the high-level connectivity. If we wanted to translate the English sentence, "active dogs eat," into Spanish, we would turn on the appropriate units in the input. We'd also have to pad the input, so it would consist of exactly 8 tokens, since these networks have fixed size inputs and outputs. I'll use a generic stop token to signal that the sentence is done. During training, we'd set the output units to represent the target Spanish sentence, "Los perros activos comen." That's roughly "the dogs active eat." In Spanish, adjectives often follow the noun they modify. And Spanish nouns usually get articles even in situations where they aren't needed in English. So here's our generic network. It's fine as far as it goes. I mean, with enough layers and enough training time and enough data, it should be possible to learn any mapping we could want from input to output. But we're definitely making things hard by not choosing an architecture more suited to the problem. For one thing, we already have a trick for making it easier for the networks to process words, at least on the input side, using embeddings. So far, the words in this network are represented by vectors of length 10,000 or so, if that's the size of the vocabulary. In particular, words are being represented merely as one-hot vectors that indicate nothing more than which word they are encoding. Lower dimensional vectors would allow the network to capture relationships between words, as we saw in the previous lecture on word embeddings. So let's modify the network to let it take advantage of word-to-word relationships using embeddings. I've added some dark blue boxes that convert the one-hot representation of words into more informative embedded vectors for each word shown in pink. Each pink vector that results is specific to the input word, with maybe 100 or so dimensions per vector. The dark blue processing boxes carry out identical computations using a shared pattern of weights. Each box maps its one-hot representation of input word into its corresponding embedding vector. I call these identical boxes subnetworks because they're mini neural networks themselves. We can train the embedding subnetworks as part of training the translation, or we could pre-train the embedding subnetworks using the ideas from the previous lesson and then install the weights. If we pre-train, the weights here would be frozen and not change while we are training the translator. Using pre-trained frozen weights means the network is less adaptive to the project at hand, but it can be trained with less data. Now we have a network that has the meaning of each individual word encoded as a vector. Next, we need a vector representation of the meaning of the combination of all the words at each point in the sentence. We would like this representation to be position independent, so it can be processed the same way no matter how long the sentence has been so far. We'll leverage the idea of creating subnetworks that can consume their own inputs. The idea of a recurrent network is for the output of some group of units to be fed back into the same group of units. Let's start off looking at the first word of the English sentence. The embedding computation produces an embedding vector, depicted here as a pink box. The green vertical box is a state vector, which captures the meaning of the sentence so far. It starts off simply with a bunch of zeros, so that there's a consistent initial value. The arrows indicate the flow from the input at the bottom to the output at the top. The green state vector and the pink embedding vector are both inputs to a subnetwork shown as a light blue box. That light blue processing box produces 2 outputs. One output is the translated word at that position. At first, we haven't seen the English sentence yet, so the output should just be padding, like the control token stop. But the second output is a new state vector that captures the revised meaning of the sentence, incorporating the additional word. And that's part of what makes this network structure so interesting. The green state vector is no longer the bunch of zeros we started with. And because we have a new green state vector for the meaning of the sentence, we can apply the blue subnetwork to it when processing the next word. The input and output words both advance from right to left, processing the words in sentence order. The network takes as input the new word and the state vector produced in the previous iteration. We run the outputs through the network a second time. Then we advance the inputs and outputs forward again and repeat step by step until the entire sequence has been processed. The reason this network architecture is called recurrent is because of the loop from the light blue box back to the green vector. Output vectors are going around and around. As a kind of processing machine, there's no problem with this kind of recurrence. It's really just like a loop in a standard programming language. But how can we train such an odd network? All the networks we've seen so far have inputs that flow to outputs with no loops in them. How can we compute a gradient that is dependent on itself? The trick is to unfold the recurrent network by replicating the piece that takes its own inputs. Then the loops are laid out in space instead of in time. Unfolding lets us go from a single green vector to 8 green vectors, one for each step of the computation. And unfolding lets us change from a single light blue box to 8 light blue boxes. And like the dark blue boxes that produce the embedded vectors, the 8 light blue boxes are copies of the same subnetwork. During training, if a weight is changed in one of the subnetwork copies, it is changed in all of them. It's trying to learn a single computation that can be applied at every iteration. It's actually a very similar trick to the convolutional patches we talked about in lecture 14. One set of weights is used in multiple places in the network. Now we have a network architecture that is position invariant. It's doing the same thing to all of the words, so it doesn't have to learn to carry out the same computation independently at each sentence position. Another thing to note is that we're not padding the network anymore. Instead, the same neural machinery is applied to each word in the sentence. We need some kind of markers to notate the beginnings and ends of sentences, but position invariance means we use the computation no matter how many words we have, so there's no need to make the network a fixed size. The same network can be used to process sentences of varying lengths. We can always just make more copies of the light blue and the dark blue computational boxes to accommodate additional words. Okay, this architecture gets us beyond a network that only translates sentences of a fixed or limited size. And there's another powerful idea that boosts performance substantially. We just need a better way to propagate information forward during processing. Let's take another look at the structure of this network. The network needs to produce the Spanish word comen as a translation of the English word eat in the context of a plural word like dogs. Take a look at how far the relevant information needs to travel to produce the correct translation. It has to be passed along by all of the green vectors. The circled green vector, in particular, has to pass along all of the information about the English sentence, which is then deconstructed to form the output words of the Spanish sentence. Since the green vector has to capture the meaning of an entire sentence, it is sometimes referred to as a thought vector. That's a bit too anthropomorphic for my tastes, but it is a vector representation of the entire sentence. And the same light blue box needs to be able to unroll all possible sentences. It's a lot to ask of any box, even one that's light blue. Wouldn't it be nice if the light blue box could peek back at some of the previous vectors? Well, it can't peek back at all of the previous vectors because the number of previous vectors varies with sentence position. We don't have a network structure that can take 5 vectors as input some of the time and 10 vectors some other time. We need a single structure that we can apply across contexts. If we separate the network by the number of inputs they take, we'd lose our positional independence property. Maybe we could use a trick like we did in the bag of words representation of texts. There, we'd collapse a bunch of vectors into one by adding them together. That would make the vectors a more uniform size, which is good, but it would also smoosh everything together. What we really want when we're producing the Spanish word comen is to look back specifically at the English words dogs and eat. We'd like to enhance the vector produced right after eat, and maybe the one right after dogs. We also like to de-emphasize the other word vectors. Once we've decided on how much emphasis each word's vector will get, we can add them together. That would be very useful information to bring to bear when selecting comen. Here's how we can enhance the vectors we think the machine learner needs to focus on while de-emphasizing other vectors. I've added 2 new kinds of vectors and 2 new kinds of subnetworks to the picture. The cyan vectors are the outputs of the recurrent network blue boxes. The orange vectors are a weighted sum of the green state vectors from the English part of the sentence. The rounded magenta rectangles near the top are ordinary trainable subnetworks. These subnetworks combine one vector intended to capture the current input word and one vector intended to capture the context to produce the current output word. The lavender trapezoids are a new kind of computation. They compare the state vector for the current output coming from right underneath of them to the state vectors from the English part of the sequence coming in from the side. The closest vectors to the green vector from below are enhanced and the others are subdued. The orange vector is the combination of the state vectors from the left weighted by which are most similar to the vector from below. This weighting is referred to as attention in the deep learning community because of the way it selectively gives attention to and enhances some of the input. It's worth taking a slightly closer look at what's going on in the lavender trapezoids, the attention selectors. It's a fixed computation. It has no trainable weights. The computation blends together the green vectors from the left and from the bottom. We'll call the vectors from the left encoding vectors, since they are constructed during the process of absorbing the input sentence. They are labeled V1 through V4. We'll call the vector from the bottom, W, the decoding vector, since it is created in the process of generating the output sequence. In one attention model, we compute the dot product of each encoding vector with the decoding vector. More similar vectors have a higher dot product. We exponentiate each of these dot product values, which greatly magnifies large values relative to the small ones, and then normalize these exponentiated values by their sum, making the values sum to 1. This operation is sometimes called a softmax because it roughly gives the highest dot product a value of 1 and all the other dot products a 0. Finally, the encoding vectors are averaged together using these softmax weights to produce the output context vector shown in orange. The weights that combine the encoding vectors together are shown as attention weights. We then sum the encoding vectors with each scaled by its encoding weight. Although this combination operation has no tunable weights of its own, its output depends on how the V and W vectors are computed. As such, it has a big impact on what weights are learned elsewhere in the network. The overall network structure is referred to as a transformer network because it is transforming sequences of words into other sequences of words. Transformers have been remarkably successful at solving hard problems in language processing. Variations on the transformer idea produce state-of-the-art translations. If we were to implement and run it on realistic data, the models would get very large and take a long time to train. Some of the best models are trained on billions of words of text and include a billion or so trainable parameters. They can take the better part of a week to train on top-of-the-line processors. A significant concern is whether the trend of creating bigger and bigger deep models is sustainable, even for the very largest companies. OpenAI analyzed the computing resources to train a top-of-the-line machine learning model as a function of the year in which their results were published. They found that from 1959 to 2012, computing resources for training a state-of-the-art machine learning model doubled every 2 years, roughly in keeping with increases in computer speed. Starting in 2012, when AlexNet stunned the world with its performance in visual recognition, the trend accelerated. From 2012 until OpenAI's analysis in 2018, the state-of-the-art machine learning models doubled in computing requirements every 3.4 months. Meanwhile, processors following Moore's law doubled only every 18 months. This trend is unsettling because it means that the only researchers that can work at the cutting edge are those at organizations with the largest computing resources. Even just the electrical energy needed to train a single model is becoming enormous. One development that's mitigating the trend toward resource-intensive computation with very few participants is that the results of these training processes are increasingly available as open-source models. Open-source models allow a wider variety of participants to use the trained models to attack other problems. That is, we can incorporate the trained models into other networks where we fine-tune their weights to solve new but related problems. As an example, we'll play around with one of the best seek-to-seek models available in 2020. This model, called GPT-2, was announced in February 2019 by OpenAI, the same organization that identified the growing need for computer power. It uses a transformer architecture, like the one we've been discussing for neural machine translation. It was trained in an unsupervised mode to simply predict text. At a time when other unsupervised language models were being named for Muppets, Elmo, Bert, Grover, the name GPT-2 was a boldly boring choice. It stands for Generative Pre-training Version 2, because it was their second model that generates text by pre-training on a large corpus. One of the remarkable things about the GPT-2 model is that it solved many natural language processing problems right out of the box, without additional training. The model was shown to produce state-of-the-art performance for a wide variety of language tasks, including recognizing names and nouns in text, answering questions, making sentiment judgments, reasoning about simple scenarios, and of course, predicting the next word, which is the task it was explicitly trained to do. By repeated applications of next word predictions, the network can solve the continuation problem I mentioned in the beginning of the lecture. The GPT-2 model was so good at story generation that its authors were concerned about releasing the model to the public out of fears that people with bad intentions would flood the internet with plausible-sounding fake text that would make it difficult to separate truth from fiction. The model consisted of 1.5 billion parameters, but for the public, they released smaller, though increasingly powerful versions in 4 stages during 2019. Let's write some Python code to use all 4 of the released models for generating text. That will let us see how the changes in capacity related to the quality of the text produced. The code for GPT-2 is maintained in a GitHub repository, so we'll clone ourselves a copy into Colab and install it so that we can play with it. Then we can download the 4 different pre-trained models that OpenAI made available, each roughly double in size from the previous. The GPT-2 code depends on a few other libraries we need to import. Okay, a lot of what's going on here is just setting up the right connection to OpenAI's code. This code does not build the network or train the network, so it's not that interesting from a machine learning standpoint. It's just providing access to the trained GPT-2 models. I'll highlight 1 or 2 of the important points. We set up a session for talking to the TensorFlow backend, which is where the high-speed numeric computations take place. We also create a space for the output of the model to go. We checkpoint the TensorFlow backend so we can establish the link to our code. Once all of that is set up, we can send our text prompt to the model for processing. We pull out the output of the model and return the string. Now we can feed a text prompt like, learning about machine learning is kind of like ... and ask the 124 million parameter model to predict the next 10 words. Each time you run it, it will do something different, but here's an example it gave me. Learning about machine learning is kind of like what you'd learn from an expert in forensic Anne. Okay, not terribly insightful, but it's definitely syntactically valid. Let's take a look to see if we can tell the difference between the 4 models. I took the prompt, my first time visiting the ocean, I marveled at, and asked each of the 4 models for a 20-word completion. The smallest model produced how big it was and how tiny it was, but it was still not quite small. The text is syntactically correct and maybe even relevant, but it's incoherent. It's odd to describe the ocean as big and tiny and not quite small. The second model produced the darkness of this vibrant ocean and at the very rugged beauty of this majestic landscape. I'd say that's a little better. The jump from the ocean to landscape is weird, but otherwise it's pretty good. The next larger model produced how beautiful it was. Sleeping on a beach is a lot like sleeping inside a... Oh, okay, it's not clear where that's going, but there's nothing particularly jarring about it. Finally, the largest model produced the beauty of the ocean and how it was further from a civilization like my own, the only one... It's actually a little bit odder, although maybe more inspiring. I encourage you to play around with the model and see what you can get out of it. It knows a lot about English and even quite a bit about the world. You can also play with one of the models online at the Allen Institute for AI's website. That version is really fun because it provides you with the top 10 highest probability next words, acting like a supercharged autocomplete. You can use the code in this lecture to experiment with your own autocomplete by repeatedly asking for a 1-word continuation of a given sentence. I decided to see how much the models know about the colors of common objects. I asked for 20 completions for 100 sentences like, the color of calamine lotion is blank, and the color of an Arctic hare is blank, without the blanks. I counted up the number of times the completion matched my own choice of color term. The 4 models performed quite differently. The smallest model only matched my choice 12 times out of 100. The 2 medium-sized models went up to 56 and 46 matches, and the largest model matched my choice 71 times. With bigger models comes better understanding of the facts about the world expressed in language. Training a state-of-the-art model to output natural language requires massive amounts of time and data. But pre-trained unsupervised models like GPT-2 are available and have proven to be adept at solving a wide variety of natural language tasks. Some machine learning researchers like Jan LeCun think that unsupervised learning is the key to building learning systems that can understand the human world. As he likes to say, the revolution will not be supervised. And because of the success of unsupervised fill-in-the-blank models for text, similar unsupervised techniques have been devised for images, filling in the missing parts of photographs, like playing Guess What's Behind the Black Rectangle? My tie. Just like in language, they learn everyday facts about common objects, like their probable colors and what other objects they tend to appear with. Similar tricks are being applied to video sequences, fill in the missing video frame, and the algorithms learn how visual scenes typically change over time. Long before Jan LeCun's pet slogan that the revolution will not be supervised, there was an old activist slogan that the revolution will not be televised. However, next time, we'll begin to see how the unsupervised revolution of machine learning is also coming to your television, and your computer, and your smartphone, thanks to machine learning's ability to generate new images. And given the new possibilities for creating images and video, the unsupervised revolution will be televised. Creating an artistic masterwork isn't that hard. At least that's what one of my research mentors, David Ackley, used to say. You just need to be able to recognize when you have something great and to be really, really patient. You want to write a great song? Just keep banging out different sequences of notes and keep going until you've got a hit. In practice, of course, having enough time is what makes this idea impractical. There are too many random sequences of notes, and most of them are terrible. If you're lucky, it might only take 5 years before you stumble on something moderately good. But most of us don't have that kind of time. Nevertheless, there's a seed of a good idea in there. We can think of the creative process as being a kind of game. One side is generating ideas, a generator. Other side is deciding if the ideas are any good, a discriminator. Machine learning can use this idea of generator and discriminator to create usable images. The generator's job is to produce lots of images until it produces one that the discriminator finds acceptable. In this lesson, we'll look at 2 different approaches to generation and discrimination. In the first approach, we have a specific target image, like this pig. Our discriminator then becomes a metric that prefers generated images that look, pixel by pixel, most like our terrific target image. In the second approach, we use a pre-trained classifier to recognize the type of image that is being produced. This approach is more like what people typically do. We recognize a general category of pigs, of which this photo is an example. So our discriminator, in the second approach, prefers images that would be recognized as being part of the pig category. Matching pictures at a categorical level is more complicated, but allows a broader range of images to be produced. In both approaches, the generator will use optimization to try to satisfy the discriminator. In the following lesson, we'll examine a third method where the generator runs without an explicit optimization step, while the generator and discriminator co-adapt, allowing the method to learn its own discriminator on the fly. But providing a specific target image is easiest, so let's start there. First, we take our pig picture, which is 64 by 64 pixels in grayscale. Some pig, right? Next, we need a process to generate each pixel for the pig image. Just for fun, I decided we're going to use pictures of some other type of object, specifically cauliflower, as picture elements to generate possible pig images. So second, we gather many pictures of cauliflower. The cauliflower images are also 64 by 64 and in grayscale. What we're going to do is use our cauliflower images to build up a single big pig image. We'll build a grid of 32 by 32 tiny images of cauliflower where the overall result is supposed to look like our target image of the pig. Our discriminator, to judge how well we're doing, will be defined as a simple kind of loss function. It takes any given large grayscale image built up from the 32 by 32 cauliflower images and compares it to the scaled up image of the pig. Then it compares the image constructed out of the cauliflower to the pig image. The comparison could be any of the distance or similarity metrics we discussed in Lesson 8 about the nearest neighbor methods. We'll use squared Euclidean distance between the two images because it's simple and produces reasonable answers. If the images are represented by matrices A and B, we take the component-wise difference between them, square those differences, then sum them up over the entire image. That means we go through all the pixels in the image and compute the square difference between that pixel in our generated image and the corresponding pixel in the scaled up pig image. The best image with respect to this discriminator is the scaled up image of the pig itself. The scaled up image of the pig will have zero loss and no other picture can do better. But what about the generator? Our generator will be making 32 by 32 grids, where each tiny image in the grid is one of 500 pictures of cauliflower in our dataset. There are 1,024 tiny cauliflower pictures in the picture grid. Finding an image from the generator that the discriminator would like is an optimization problem. Our approach to this optimization problem would be to just keep asking the generator for images and keep track of the one the discriminator likes the best so far. But that's just the idea of being super patient, and that would be really, really, really slow. The set of possible images the generator can produce is 500 cauliflower choices raised to the power 1024 for the 1024 pictures in the grid. That makes a number with roughly 2,700 zeros. We'd like to find the generated image with the very best score, but we will not have time to find it this way. Fortunately, the loss function used by our discriminator decomposes into 1024 simpler optimization problems. The best composite image consists of the best choice of cauliflower image for each of the positions in the grid. So for each position, we can just loop through the 500 cauliflower images to see which one is closest to the corresponding patch of the scaled up pig image. The code for solving this optimization problem runs quickly. Instead of checking all 500 to the 1024 grids, it just checks each of the 500 images 1024 times. When we run it, we get a pretty good likeness. Many restaurants are looking for ways of replacing animals with vegetables on their menus. Maybe the cauliflower pig could help them get started. This approach to image generation demonstrates the fundamental recipe for machine learning that we've been using throughout the course. There's a representational space, which is the set of 32 by 32 grids of cauliflower pictures. There's a loss function, which is how far away the composite image is from a picture of a pig. And there's an optimizer, which searches the space of cauliflower grids to find the best one. There's even data, unlabeled, in the form of the set of available cauliflower pictures. There was a 16th century Italian artist who painted portraits of people consisting of all sorts of vegetables, fruit, flowers, fish, and other objects. We could follow his lead using a wider variety of objects in our input data, and we could draw our pig that way. Or we could use photos of our friends or beloved celebrities and combine those images to build any target image we want. The images we can generate with this technique are limited only by our input images and by our choice of output target image. We get to be creative, but the machine learner, not so much. When we pick our target picture, at best, we end up getting something very similar back. To output a broader, more creative set of images, it would be nice for the discriminator to be a little more open-minded and allow the generator more freedom in creating acceptable images. For example, if the cauliflower pictures came together to look kind of like the pig Babe from the movie, the discriminator we have at the moment would dismiss it out of hand. Even though that output would look like a pig, it would not look like our target pig. But how could a discriminator judge an image in a meaning-based way? We could use image classifiers, which are trained to recognize images in terms of their category. So instead of a pixel-based discriminator that prefers images that match a specific target image pixel by pixel, let's consider a discriminator that employs an image classifier. A classifier discriminator, as the name suggests, prefers images it recognizes as being in a specified class. To save time, instead of building a classifier from scratch, we'll use a pre-trained classifier for a set of 1,000 ImageNet classes. Specifically, we'll make use of the VGG16 network we also used in Lesson 14 on vision. It's a high-quality classifier that recognizes pigs and 999 other categories of objects. We'll start with a generate and test approach. Let's say we want a picture of a flower, a daisy, say. We could have the computer generate an image, then run it through VGG16 to see what class the network thinks the image is. Is it an ox, or a lampshade, or a daisy? We'll keep track of which image is recognized most strongly as being a daisy. Then after many attempts, we can display the most daisy-like image. Let's try it out and see what we get. We'll load some of our favorite packages. We'll import NumPy for working with vectors. From Keras, we'll use the VGG16 package. We'll also load a package we haven't talked about before called the Keras backend. It will let us tinker with VGG16 at a slightly lower level than we needed to before. We can then load the pre-trained VGG16 weights as our model. We need a few more packages, a carriage library for manipulating images, and the code VGG16 uses to pre-process images and make predictions. We'll make a routine for producing a random image, suitable for presenting to VGG16. Let's call it randimage, and save its output as IMG. The result doesn't look like much to me. It's just a bunch of colored points. But what does VGG16 think it is? Looking at its top 10 predictions, the class it thinks fits best is envelope. But it only assigns 9% probability to that class, so it's not really very confident in its choice. It does seem to think it's some kind of fabric or weave based on the other classes in the top 10. Bib at about 9% confidence, followed at some distance by velvet, binder, and handkerchief. Daisy is not in the top 10. How daisy does VGG16 think the image is? The daisy class is number 985 in ImageNet, so component 985 of the model prediction is its belief that the image is a daisy. What's the score for this image? About 0.01%. That is not very daisy-ish. In fact, it's on the anti-daisy-ish side. There are 1,000 image classes, so a completely uncertain prediction would assign each class 0.1%. The daisy score for this image is merely 1/10 that amount. But maybe it's good the score turns out to be so low. After all, it doesn't look like a daisy, does it? But even after 1,000 attempts, the highest daisy score is still just 0.02%. That took about 10 minutes of runtime. It seems pretty hopeless that a daisy picture is going to emerge anytime soon. But we have a secret weapon that we're not using. A classifier based on a neural network like VGG16 is not just a black box. We don't have to confine ourselves to asking how daisy the classifier thinks an image is. We can also ask it, what change to this image would you propose that would make you think it is more like a daisy? In particular, that's precisely what gradients do. Gradients are slopes, measures of how much a change in one variable would result in a change in another variable. In this case, we want to know how a change in the image would impact the network's prediction. Neural network architectures are built specifically to allow gradients to be computed. We've used gradients to train neural networks. We ask, what change would you like to see to each of the weights so that the resulting network classifies images in a way that's more consistent with the training data? Then we bump the weights in that direction and repeat. If we take enough small steps, we'll find a local optimum in weight space. But for image generation, we don't want to change the weights. What we want to change is the input, the image, so that it is the sort of input that produces the particular desired output. Neural network training and image generation are different problems, but they're not that different. Both use the same gradient computing machinery. Here's how we'll compute gradients to search for an input image. First, let's grab all the names of the VGG16 layers for easy reference. The target class number for DAISY is 985, which I looked up in a set of ImageNet classes. We're going to need to represent the function from input image to class in a form that will let us take the gradient. The input is the input layer of the model. The word tensor here refers to a generalization of vectors and matrices. The set of input weights is a tensor. The output X is the activation on the prediction layer for the target class of daisies. The objective we want to optimize is exactly the daisy activation output. The more daisy, the better. We can now take the gradient of the objective with respect to the input. We use k.gradients with respect to our objective of the input tensor, and then we store the results in the variable grads. It turns out that the magnitude of the gradient will be very tiny. So to help boost things along, we'll use a trick of normalizing the gradients. Not very elegant, but it will save us a lot of computation time. Now we link the input image with the objective and the gradient. We're ready to optimize the image. We'll keep going until the image is 99.99999% daisy. That should do the trick. It'll be our answer true. Now we'll run an iteration, putting the image IMG in and computing the objective value and the gradient. We'll print the objective value and then add the gradient to the image to move it towards greater daisyhood. Here's how it runs. Once again, we start off with a daisy score of 0.01%. But even one update brings us up to 0.08%, which is 4 times more daisy-ish than the 0.02% we got by random generation and test. In 16 iterations, it has created an image that convinces the VGG16 network to within machine precision that it is 100% that daisy. Perfect! Okay, let's unveil the most daisy. It looks pretty much like what we started with. Well, no, not quite. There's streaks in the speckled background that look kind of like petals coming out of a flower? Maybe? The image is indeed visibly altered, but it's not the sort of thing anyone would confidently declare to be a daisy. And yet, here's this world-class object recognition system saying the image is absolutely positively 9/9 sure that it is a daisy, and nothing else. Interesting. There are 3 things to learn here. One is that VGG16's understanding of objects is, well, alien. It can reliably classify photographs, but it is also picking up on cues in images that are very different from what matters to people. But it's also worth noting how quickly the gradient approach was able to create the image. It really is a powerful way of doing optimization. The objective function wasn't what we wanted, in that an image can score very well on the metric it was given without looking like a daisy to us. But the optimizer quickly did its assigned job of finding something that the discriminator would like. A third thing to learn is that the network became very convinced the image was a daisy after really minimal changes to the overall initial image. What if we'd started with something other than random speckles that the network thought looked a little like an envelope? What if we'd started with an image that it recognized as something else? Let's try an example. I downloaded an image of a goldfish and asked the program to turn it into a goldfinch, the bird. The optimizer ran for 4 iterations and produced this image. It's the same picture we started with, which VGG16 thought was a goldfish, but now the network sees it as 97% goldfinch. Here are the before and after photos for comparison. They are, for all human intents and purposes, indistinguishable. And it's not like we fooled it into seeing a goldfinch slightly more than a fish. Its second and third choices are also songbirds. It thinks this photo is a bird, and it's 97% sure that that bird is a goldfinch. But why is VGG16 97% sure of itself when, from a human perspective, it is so clearly wrong? When such a generally accurate system says it's 97% sure, we don't expect such a huge, nearly total miss. No one in machine learning is entirely sure why the networks act this way, but they seem to be paying more attention to fine textural details than people would. If you look really closely, you can see little speckled streaks, kind of like what appeared in the fake daisy image. These patterns are probably the cue that the network is latching onto to imagine it is seeing a bird. I believe that a person could study these images intensely and start to recognize the cues, but it would take a lot of practice. Computer security researchers refer to these sorts of images as adversarial examples because they're created explicitly to fool a classifier. For instance, experiments have been performed with adversarial examples to show that self-driving cars can be tricked into recognizing a stop sign as a speed limit 45 sign. Now, I'm not aware of any attempts to deliberately fool a real self-driving car, but given the reality of malicious activity on other computer systems, we have to become prepared for all kinds of malicious activity. Such examples show why it's hard to produce human-recognizable images from scratch by exploiting image classification networks. While almost every goldfinch image is recognized as a goldfinch by the neural network, not everything that glitters like a goldfinch really is a goldfinch. But the more our image generation is constrained, the more it can make better images. Since image classifiers have a kind of high-level understanding of an image, we can use a classifier to intervene on images in a semantic way. Let's take a look at an interesting technique called style transfer that leverages this idea using a reference image. Consider a photo of the Manhattan skyline rendered in the style of Van Gogh's Starry Night, for example. Adding swirls and artistic flourishes can give a sense of Van Gogh's style. We can think of this image generation problem again in terms of searching for an image that minimizes a loss function. But here, the loss function includes similarity to both the content image and to a stylistic reference image. Let's try an example, looking at two portrait images. Our content image will be a photograph of a face. Our stylistic reference image is in Roy Lichtenstein's pop art style. We'd like an image of the same face, only with some of the features that make Lichtenstein's style so recognizable. Maybe the hair could be made more solid with more use of strong primary colors. Maybe the face and other skin could be rendered with dots. Let's start off at a high level before we get caught up in code. We'll define a loss function that is the sum of three kinds of loss. A content loss that's about making the new image recognized as being the same as the content image. A style loss that's about making the features in the new image match those in the stylistic reference image. And a local variation loss that discourages the new image from being too speckled by penalizing local variations in the image. We'll then have the computer search for images that have low combined loss across these three categories. Let's take a look at each of these loss categories in turn. There's a lot of details, so I won't go through everything at a low level, but you have access to the code, so you can look through it and run it and get a sense of why it is structured the way it is. The content loss is the simplest. We're comparing a base image, the face, with the combination image, the new image being generated. The comparison takes the difference between the two, squares them, and sums up those differences. That's precisely how we measured content loss when we made a pig out of cauliflower. There are two important differences, however. First, the k.sum and k.square functions might seem a little strange. We're not just using the standard Python built-in functions for these operations. That's because we're not actually calling sum and square. We're building an explicit representation of the computation that uses sum and square. We need an explicit representation because we need to be able to take the gradient of the loss computation with respect to the image. K.sum and K.square create a kind of computational graph that keeps track of what computations need to be made. The deep learning package can then run these computations forward as normal, or the package can run the computations backwards as part of the derivative computation that figures out how the outputs change the inputs. You can't run normal code backwards, so these specialized routines are used. The gradient computation itself is hidden inside the deep learning package. On the outside, the code looks almost normal. The other important difference between what we're doing now and the cauliflower pig example is that we're not going to compare the images at the level of pixels. That's too literal. We want the system to have a bit more artistic license, but without falling into the pitfall of dreaming of our electric images in a way that is so alien that we don't see the connection to real-world objects at all. So we're going to compare the images at the level of one of the internal convolutional layers of the neural network. Which layer should we pick? Well, the choice is somewhat arbitrary. but it's also trying to solve a balancing act. In particular, different layers of the network capture different levels of abstraction in the analysis of images. The closer the layers are to the input of the network, the more these features capture surface aspects of the image. What colors are in what places? The deeper into the network we go, the more semantic the features appear to be. Is there an eye somewhere in the upper right of the image? The second layer of the fifth block of weights in VGG16 is a compromise between capturing features that are too low-level and features that are too abstract. The code extracts activations at this layer for the base image and the combination image, and it uses these activations in the loss function. As for the style loss, we'd like to measure loss in a similar way. No one has noticed anything like an explicit artistic sensibility layer being learned by VGG16. And yet, features that capture some aspects of style can be extracted from the network indirectly. Here's how we're going to do it. We're going to look at the feature representation the network is using across a set of different layers. Specifically, we'll be using the first convolutional layer for each of the 5 blocks of convolutional layers in the network. We construct a feature vector out of these activations created by both the stylistic reference image and the new image. These are the vectors to be compared by our style loss. At its heart, the style loss follows the same structure as the content loss. Take the image being created and the target image and compare them by squared Euclidean distance, total least squares. This quantity is scaled, but it's the same loss structure as what we've seen several times already. The content loss and the style loss do apply to different feature vectors. And style loss also differs because it transforms its feature vectors into something called a gram matrix first. A gram matrix is a representation that captures similarities between objects. In this case, we're comparing the patterns of activation of a specific convolutional filter across the image. The style loss is minimized when the two images have similar gram matrices across all the chosen convolutional layers. Style loss wants the patterns of convolutional filter activations to match, meaning that the same low-level features activate together in the same regions. The final component of the loss is due to local variation in the image being created. It's not a function of the content image or the stylistic reference image. The loss's goal is to penalize the image for being too speckled, essentially charging it for rapid changes in color between neighboring pixels. Here's how it works. It takes the image and chops off the first column. Then it takes another copy of the image and chops off the last column. It lines up those two images and calculates the pixel-wise squared difference between the two copies. It sums up those differences shown here in black. The same operation is repeated by deleting the first and last rows to compare things in the vertical direction. A completely solid image would have no local variational loss because the shifted image would still match perfectly. A speckled image would have high local variational loss because every pixel is next to a pixel of a different color. Basically, the more that the pixels form large, solid colored regions, the lower the loss. In code, X represents the created image. X has its first and last row removed and subtracted. X then has its first and last column removed and subtracted. Both are squared so that both negative and positive differences are penalized. We slightly enhanced differences by raising them to a power of 1.25 before summing. These three losses, content loss, style loss, and local variational loss, are all summed together. The optimizer is asked to create an image, an input, that minimizes the weighted sum of these loss functions. The actual code looks pretty similar to what we did when we were trying to make a daisy. We have Keras compute a gradient of the loss function where the input image is the variable. Then we repeatedly update the image in the direction of the gradient and repeat. The effect is pretty interesting. The content image is on the left and the stylistic reference image is on the right. After the first few iterations, we can already see things happening. The smooth skin tone in the content image has been replaced with dots, similar to those in the stylistic reference image. In fact, there are dots of colors everywhere in the picture, including on the hair, background, and clothes. Tiny patches of yellow are visible, presumably to match the style of the yellow hair in the stylistic reference image. More yellow is visible now. Unfortunately, it doesn't limit the added yellow patches just to the hair. With the code we supplied, you can try various other combinations of content and style to see what happens. There are lots of interesting examples online, and you can also experiment with your own personal photos. It's fun. 10 iterations took me about 20 minutes to run on Colab. Creating images at the level of a real artist is well beyond what we can do in 2020. But the representations discovered by deep neural networks make it possible to generate intriguing novel images. A powerful generic approach we've seen is to have a generator that makes images, a discriminator that judges them, and then for the generator to optimize its output with respect to what the discriminator is looking for. The choice of discriminator leads to different kinds of images. Semantic discriminators that pay attention to the meaning of the image can be defined by leveraging trained image recognizers. Stylistic transfer has also been used in other modalities like speech and video. For example, neural networks can be used to create deep fakes, in which actual video of a person is combined with video of someone else performing an action to make a video in which the person is performing the action. The artistic opportunities are immense, but there's also a risk of deep fakes being used to mislead or discredit. Taking gradients with respect to images provides a mechanism for synthesizing new images, made possible by a sharing of low-level stylistic features. In the next lesson, we'll see how neural networks can be used to create photorealistic images. The idea is to make both the generator and the discriminator improve by having them battle head-to-head for supremacy. This arrangement, which is generating images of people and places that have never existed, is called a generative adversarial network.